you guys to pick up the skill sets to solve the real problems. So today we are gonna have two training sessions for you. In the morning is about natural language processing. So definitely it's very useful. And in the afternoon we have a deep reinforcement learning, which is very sexy and fancy. It has a lot of potential. And I cannot wait to introduce the instructors of this morning. So SK Reddy. So Mr. Reddy is a techie and entrepreneurs. And currently he is a chief product officer in digital group and network. And before that, he was a co-founder of a few startup companies. And he was in Apple company for a few years doing product management. He is also the blog writer, covering a lot of hot topics, AI, machine learning, NLP, IoT, also the recommendation systems. So ladies and gentlemen, let's welcome SK to teach us how to deal with NLP.
Thank you. Thank you. Thank you very much. Good morning, everyone. Thank you for coming for this session. I'm very excited to talk about this. Before we get into the topic, a few announcements, kind of. I tend to speak very fast. If you see me talking very fast, please let me know. I'll slow down. Second, I guess you know the location of the restrooms and outside stuff. If you have any charging problem, the gentleman Mike there at the end, you can flag him and maybe he can help you with the charging and any stuff you're going on. Let's talk about the biggest focus, the installation of the software and files which I had sent. The instruction email was sent yesterday night. It was purely my mistake. It's not the organizer's mistake for the delay in sending it to you. If you have installed the PyCharm and Anaconda, that's fantastic. Or if you have other tools, open source tools which you're using to run some Python files and the Jupyter Notebook files, that's fine too. But most importantly, please don't worry about if you're not installed completely or if the files are not running on your computer. We will be having the video recording of this session posted, at least on my personal YouTube channel. You can go back and look at that, and the files you have downloaded, you can install it correctly later on and then work on it. The reason for that is the most important fact of NLP and the most important takeaway for today for all of you is to understand the concepts in NLP. Those are a little bit difficult and the most important ones too. Because of the advent of so many frameworks coming in, programming NLP solutions is becoming easier and easier. There will be a day eventually where it becomes almost trivial. But for picking the right model, right hyperparameters, right way of training, right type of data, right type of looking at the data, all of these needs understanding NLP conceptually. And you need to do a little bit of out-of-box thinking sometimes too. And sometimes the data doesn't show you the right solution, a right path, and you got to look for different data. And before I start NLP, I want to tell you a story. You guys like stories? A few years ago, the Pontiac division of General Motors company got a mail from one of the new car buyers. The complaint the customer had was so silly that they just threw the letter away. They said, it's some prank. The customer wrote another letter 2 weeks later, and he explained again, you know what? I have sent a letter earlier, you did not respond. I can imagine it sounds very silly. For me, even it's silly because here is the problem. Every night after dinner, we as a family go to buy ice cream from a nearby ice cream store, come back and eat ice cream. We buy different type of ice creams every day. Sometimes it's vanilla, sometimes it's something else. But here is the interesting part. Every time we buy vanilla and get back into the car wouldn't start. Every other ice cream we buy, the car starts perfectly fine. We come home and eat ice cream. And I thought it must be just a fluke. So I tested it multiple times. And it happened so many times, now I think it's a concrete evidence that there is a ghost in my car which doesn't like vanilla ice cream. So if you get that as a data point to do an analysis of what's happening, what would your response be? Collect more data. Okay. Yeah, I know this is not an NLP problem, but the point I'm trying to make here is sometimes when you look at the data, you just wouldn't get the story by just looking at the data. You've got to do a little bit of processing of the data. Anyway, so Pontiac division, they said, okay, we've got to find out what's happening. So they sent an engineer. Are you all engineers? Okay, good, good, nice. I like engineers. I'm an engineer too. So what would the engineer do? He goes and verifies whether the complaint is correct. So every night, he takes a ride with them, go to the ice cream place, and then come back with them. And lo and behold, every time they buy vanilla ice cream, the car wouldn't start. So the engineer is now confused what to do. But then, being an engineer, you just can't believe there's a ghost sitting in the car. So he started making notes. He actually started collecting data. What time we left, what time we reached, what's the distance, how long we stayed there, what is the weight, number of people in the car, is there any problem in the pollution or whatever of the car. After a few days, he figured out one anomaly in the data. Every time they picked up vanilla ice cream, they come back into the car within a few minutes. Every other ice cream takes a long time because vanilla ice cream is the one which is so popular. They keep it just outside near the door of the store. You just pick it up, pay, and get out. Whereas all other ice creams, you got to go inside. He said, okay, now I have a different data point. The time it takes from the time you turn off the engine to turn on the engine is different the days you buy vanilla ice cream versus the other ice cream. So it's no more ice cream problem, it's just a vapor lock problem. If you turn the engine on immediately after you turn off, there's a vapor lock and an engine wouldn't turn on. So, welcome to NLP. I would be talking about so many different concepts that's being used in the last 2 or 3 years. And when you are presented with data, you would be using these concepts to find solutions. You could be working for a healthcare company, you could be working for a hospitality or transportation, manufacturing, port management, energy trading company. It could be any company, and you have a variety of data. You could have statistical data, you have the textual data, you have the image data, and then you have the audio data. Some of the concepts we'll be talking today will be also applied in a little bit of image processing and a little bit of audio processing, but we will be focusing more of text processing, natural language processing. One more time before I get into the presentation, if you are not able to install, if you are not able to run the applications along with me, don't worry. Focus on the concepts, and you can always run them when you go home because we'll be having the video recorded, posted maybe in a week or two, not more than that, maybe a week. I want to share the PowerPoint after the presentation is over because based on the feedback I get, I normally update it, make it a PDF, and share it with people. There's a lot of information. Sometimes it's not useful. I may not be covering all the stuff I have. I actually have 8 hours worth of stuff, and we have only 4 hours, and after that you got to leave, I guess. Yeah, you can't be looking at my face for longer than 4 hours. So I'll not be able to share the PDF, PPT right now. After we'll be. So when I uploaded the YouTube video, I'll also have the PDF file uploaded. So that's my company. So these instructions you already seen. You have installed NLTK successfully. This is the GitHub link. I think you may all have seen, and hope you have installed the files I mentioned there. So let's start NLP. Let me give an example of a statistical problem in machine learning. We may be solving one statistical problem too, just to talk about a Keras model, but let's say you are a retail company and you want to do an email campaign to attract more customers. And you collect data after the campaign is over to check how many people responded positively or not. And if your verification is how many people actually came within the first 2 weeks after the end of the campaign, and if that shows the success of your campaign, you want to find out, using machine learning, what factors facilitated, what factors did not facilitate. So the customer information like gender, age, location, spending habit, maybe job, you could have a 10, 20, 50 features that's being used. And you can use any of the tools you have, whether it's a support vector machines or boosted trees and XGBoost, whatever. And the computer can process the number. But in text, you've got to do something different to process a text. And some of the problems you find in text is, actually there are a bunch of problems. Words sense disambiguation. For example, the paintings were stolen by 4 thieves. They were caught the next day. They is what? Are you referring to the paintings? Are you referring to the thieves? Similarly, pronoun resolution. That's pronoun resolution, and word sense disambiguation is, Donald Trump went to Asia along with his team. He met with the prime minister. Obviously, he here is Trump. So when you do an analysis of the text, you need to get out of that ambiguation, the ambiguities in the text. Now, what's the use case for that? Why would you want to do that? I'm facilitating, I'm actually an advisor for a startup company where they manage legal contracts. I was told big companies like IBM, Microsoft, Apple, Google, they typically have around 40,000 to 50,000 contracts every year. Now, you can't have a legal team of 100 people even to manage those contracts, especially if there's an actionable clause in a contract. You have to go back, you'll be having multiple people going back and reading the contracts constantly. They're developing an automated solution which will process all the contracts, identify actionable clauses, and based on relevant triggers, it actually takes an action. The action could be as simple as send an email to the legal team, or send an email to the CEO, ask the supplier for a penalty payment, or inform the vendor management to do an audit, whatever is the the actionable clauses. In such situations, you can use this type of processing of text. Of course, healthcare is a major investment focus area. If you really want to start a startup company, healthcare would be a good idea because you'll get funds immediately. Because every venture capitalist is investing money with companies trying to do ML solutions in healthcare. And healthcare is a massive area where there's lots and lots of text being used, the unstructured text. When you go meet the doctor and you as a patient is discussing your situation and the information you're sharing with the doctor, many times the doctor is actually typing information. In the typing also sometimes he loses or he makes grammatical errors, he makes other errors, or he misses some information, he or she. And if you have such a text which is not completely populated, sometimes erroneous, sometimes grammatically incorrect, sometimes some missing information, how would you process that to have an actionable item? There's a company in London, DeepMind, Google actually worked on, it's called, I think, live streams, if I remember correctly. They're working with a healthcare company based on the unstructured information of a patient. It sends an automatic information on a page to a doctor or a nurse or a pathologist or whoever it is, based on the situation that the patient is going through, especially if the patient is in ICU care or some other care, based on the current information that's coming in, which actually helps in cost cutting and all that stuff. What types of processing can you do? There's so much of processing that you can do on the text, and almost all of this processing is automated now. You can just run a few API calls using some of the frameworks available. We are going to use one framework today, but there are other frameworks too, open source tools available. You can do the processing. But there's so many things. For example, tokenize. If you have a long text, you want to identify individual words. Each word would be a token. You want to stem. Stemming and lemming is a field where you can shorten the word to its root. When do you use that? You use it when you're doing a language translation or sometimes even summarization. I'll talk about that in my presentation today. But stemming, lemming is another one. Sentence segmentation. If you have a long sentence, you want an automated chunking or segmenting of a sentence into smaller pieces, which are many times grammatically correct. For example, I took a morning flight which normally departs at 6 a.m., which did at 7 a.m. today, and reached still on time to my destination. If that's a sentence, if I want to know what time was your flight departed, what time your flight departed today, if you do a sentence segmentation and then do a little more rules engine, you can actually find out what's happening. Word segmentation too, instead of a few words together as a sentence segmentation, you can actually find word and pieces of words being made into small pieces. Parts of speech tagging. Every sentence has a noun, verb, adverb, pronoun, preposition, so many of parts of speech. You want to identify what was the root word, and if the root word happens to be a verb, what was the subject that is working on the verb. For example, John went to the movies. Went being the verb, being the root. It says, okay, which word, what is the subject that's working on this verb? It actually recognizes that. I'll show you a picture of how graphically you can do a tagging, and then you can do a processing, or you can write a bunch of rules. Or John did not go to the movies. So you actually have the not modifying the go part. So you want to identify the verb and you want to identify the modifier of the verb to automate the processing of the text. Chunking is again, I think, identifying the pronouns and nouns in a sentence. Named entity recognition. If you have a big text, you want to identify names of people, names of organizations, names of locations identified, and you can do a little bit of a parsing on it. Now, if you know the name, why can't you just do a pattern recognition? You can do that too. But then, if you know the name, if you know what you're looking for, then you can go find using just a pattern recognition. But if you don't know what you're looking for, you know that some location is being mentioned and you know some person is being mentioned. Obama was the last president of this country, and if there's another sentence, Harvey Weinstein got into trouble. If you don't know what the noun you're looking for, then it actually parts of speech and named entity NER will help you. So there's so many other analysis. Co-reference resolution. I showed an example too. He went to the movie, and if you have a previous set of sentences, who is the he referring to is sometimes confusing, because you need to replace those references by the original subjects or nouns, so that when you pick only one sentence and process or take an action based on it, you have the complete information. You had a question?
Yeah. In the case of name entity recognition, can I update my own, suppose my company's name or my customer's name?
Yeah, you can train the library. Typically, you have NER, which is based on, let's say, NLTK or Stanford NLP. They all are trained to identify the most commonly identifiable names and locations and organizations, but you can also train further to make it specific for your organization, or with your names or your organization's names or locations specifically, yes. This is an example of tokenization. If you have a sentence, and I'll show you also, I'll make you do a tokenization example, but this is what typical tokenization means. You break the sentence into individual words and the other notations in the sentence. Lemming and stemming is this. If you have an original sentence, this was not the map we found in Billy's Bones chest, and when you do the Lemming and stemming, it says, "The were not the map we found in Billy." Now, this is lemming and stemming, as I mentioned to you earlier, is used for when you're extracting intent and you don't know exactly what the intent is and you want to go back and verify based on the root word. You need the root words. Number one, when you're trying to do language translation and some summarization, you need to have the lemming and stemming. Yeah, those are the two use cases I can think of.
Many people know what stemming is. Lemming, you usually think of a small animal like a mouse. Explain more about that.
Lemming and stemming, I normally talk together. It's actually trying to bring the word to the root. I may have an example, and I'll talk about that lemming, what the lemming means. But I don't think I'll be able to explain it in words. Maybe if I show it to you. This is, I'm using Core NLP here. It's not NLTK. I've asked you guys to install NLTK. That's one of the older and a longer time NLP open source tool available. Standard Core NLP or standard Stanford NLP is also one. Stanford NLP uses Java, and I wanted to use Python also because of two reasons. One is, of course, my personal preference towards Python. Number two, if you look at all languages being used in machine learning nowadays, I think Python is the most popular in terms of number of people use, number of contributions, the richness of tools available, and the variety of frameworks that use Python. So that's the reason why I've used NLTK. But you can use Stanford Core NLP too. So that's core referencing. It's identifying showed of his, and it replaces the word his with the name of the person who the sentence is referring to. This is basic dependencies, where it includes the parts of speech tagging, but it actually parsing the sentence to identify the dependencies. If you look at, I would give you a couple of seconds. Look at the sentence, President sorry, I cannot pronounce the name correctly. Xi Jinping of China, on his first state visit to the United States, showed off his familiarity with American history and pop culture on Tuesday night. It's a long sentence, multiple pieces of sentences there. If you look into how, and if you run this, there's a browser-based API for NLP, and if you copy-paste any sentence there, within a few milliseconds, you will find this type of dependency matrix identified. And you can actually use this to identify what's the root word, what's the verb, what's the preposition, what's the noun, what is modifying what is determining, what words determine what other words in the sentence. All of the information is provided right there. And then if you want to process it for your business use case, you have to write the appropriate rules and then and extract the words you're looking for. Open information extraction is another part of Stanford Core NLP tool. What it does is, if you have a complex sentence, it breaks that into tuples, mostly binary three tuples, which is actually a combination of words, which many times makes sense if you just read it independently. So that's the first step it does. So it breaks the sentence into 2 or 3 pieces, each piece being multiple words. And then from then it starts giving the bare minimum most important words which communicate the essence or the message in the sentence. Sometimes it gets it wrong, which is the case for every tool. But if you look at the starting sentence and if you look at the final 3 tuple words at the bottom, it captures the essence of the message. Sometimes if you have a long sentence, as I mentioned to you earlier, if you have critical 2 messages or 3 messages, it may lose that part. But if you have a single message in a sentence, it actually breaks it down very nicely. Parts of speech tagging, there are hundreds of ways of tagging. The coordination, conjunction, cardinal digit, determiner, existential there, foreign word, preposition, adjective, adjective comparative. There's so many tags available. So if you have a linguist in your organization because you have lots of text coming in and you want to process the text, and you can define a bunch of linguistic rules you want to, this makes it fantastically easy because the tool is giving you all the parts of speech tagging of a sentence or the bunch of text which you need to process. So if you are a manufacturing company and if you have information about your product, or if you are, there's a nice case study about, I think it's called Standards Organization, which publishes summary of 10K and 10Q reports filed by public companies. It actually does a summary analysis of how good the quarterly announcement by company ABC or the annual announcement by the company ABC is good. So it actually does the analysis and publish it. Right now they are doing it completely manual. So what they do is per month they can only do around 100 reports because they just can't afford to have more number of people. But after they started using NLP, which includes your NER and parsing and other stuff, they actually can do 450 or 500 reports on a monthly basis. So 5 times productivity. That's another use case you can think of if you can break the text down and process it using rule engines. When you download NLTK, I'm sure you all have done, NLTK is one of the most commonly used by many academics, and they've been using for the last so many years, I think 5 or 10 years at least. For you to do lots of experimentation, I think you should do it when you go home today, because you're so terribly tired of listening to me in the evening. Take a rest, but when you do it tomorrow or the day after, there's so much of corpus of information available, so many books and text available you can process. I think we're going to be using a brown corpus today for some of the processing, but there's so many books available, so much of text available. So if you want to do any type of processing, just experimentation, those are the resources available. Okay, so let's open a Jupyter notebook. If you guys have, what I'm going to do is I'm actually going to go to Anaconda, going to open a Jupyter notebook. Again, if you cannot do it, don't worry. The files are extremely simple files, and I'm trying to show, for at least for the next 2 or 3 hands-on activities, a very, very simple processing of text, just to show how extremely it is simple, even though it's using lots and lots of text. Sorry? For the Wi-Fi? Okay. So that's the password. Okay, you guys can take a picture of it so that you don't have to forget and stuff. Okay, let's go back. Okay, so what I'm going to do is I'm actually going to show you, so I'm importing NLTK. I've already done it a few times, so it may show that it's already done. Yeah, it's already done, but it takes 2-3 seconds to download. If you have not done it, what happens is when you said import NLTK, it actually has a pop-up screen asking you what type of resources you want to download. Say click all and button download, and it just takes 2-3 seconds, not more than that. The entire text will be downloaded there. Then what I'm going to do is, so I'm going to do this. Okay. I need a Wi-Fi. Okay, so this is the pop-up screen you get. The default is, I think, selected all. You can pick 1 or 2 if you want, but I would recommend select everything and click download. Okay, it just takes less than 2 seconds. So I do this, I go back. Now I'm going to actually show how a POS tagging is done. So I'm actually going to pick a random sentence, and I'm going to run. Okay, sure. How about this? I can make a, how about this even? Better? So I'm going to go this and, oh, not this. It just takes a millisecond, hardly a few milliseconds to do the POS tagging. So if you have a pipeline, let's say if you have a Spark, Apache Spark, and if you have a series of text coming in, and if you want to do parts of speech tagging on it and then do further processing downstream, it won't even see this taking any time at all. Sorry? Raise your hand, please. I can't see your face. Yeah. I can't hear you. Bigger. Okay. The file is in the GitHub, but you need to open the Jupyter Notebook using Anaconda. Yeah, yeah. So is this better, the text size? Okay, thanks. There is a, you have to click download and it actually downloads, and you have to close the dialog box. Okay. This is not a file, and I'm just opening a Jupyter Notebook. I'm copy pasting the instructions from the my presentation. So if you can just write the text, whatever you see it on the screen, onto your Jupyter Notebook. So that's one example. There's another example I can just do just to show how quick. So there's another sentence. They refuse to permit us to obtain the refuse permit. Now here is the interesting part, especially in NLP. If you have parts of speech tagging or NER or parsing, here the word refuse. Look at the word refuse. One is a noun, one is a verb. And let's see if it can figure it out. Okay, can you imagine how wonderful that is? The first refuse, it figured out it's a verb, a proper verb, VBP, and second refuse, it figured out it's a noun, a singular noun. Isn't it amazing? Isn't it just completely amazing how it figures it out? Unless you have text from a domain-specific text, like let's say healthcare text. I was talking to a gentleman by name David Talby, a very smart guy. He was the CTO of a healthcare company. He mentioned the English language has a vocabulary of 500,000 tokens, unique words being used, typically what we speak or we write or we read in books and stuff. Do you know the size of vocabulary in medical domain? English words, not the words derived from Latin and other stuff. Do you know how many words are there? English words that's being used in medical domain. Regular English language, what you and me speak, is 500,000 tokens, 500,000 vocab size. 50,000? Okay. Any other guess? 5 million. 5,000. Someone said 5 million. 10,000. Okay. Someone said 3 million somewhere there. 3 million, you said? Okay. Any other? It's actually 3 million. 3 million words. Of course, they have actually created newer words which we don't use in the normal walks of life. We don't normally use that. But there are 3 million terms. But here is the complication on top. If you're working for a healthcare startup and are trying to do ML or using NLP on that, here is the complication. First of all, you have a lot more words. And of course, you have a bigger corpus you need to use for training. Doctors don't write the complete word when they're making a report. Sometimes they write an abbreviation. Sometimes they make a shortcut. Sometimes they may just have the shortcut which does not even refer to the original word, because the hospital in the 5th floor, you have a same team of 4 or 5 doctors, 10, 15 nurses, all working together for the last 4 or 5 years. They know exactly what the doctor is saying, and hence he will just say, hey, have you done X1? It could be whatever it is. X1 could be any damn thing. But, sorry for my French, but then comes the complication of how would you use NLP in such a context? PO is talking will fail there because it does not know what X1 is unless you have enough corpus of text to show what X1 is. But there are other rule engines which companies use, and we can talk about that if you guys are interested in offline. But that's the extra complication of okay, let's try to do another a simple use case. In a big, massive book, let's say, Shakespeare's novels. Have you guys read Shakespeare's novels? Yeah, wonderful. I'm actually going to show the result of a deep learning model which actually writes like Shakespeare. Shakespeare is dead, I guess, right? Isn't he? Yes? No? Dead, yeah. At least, I'm sure at least he's dead. So this model actually writes stories like Shakespeare because you can actually train a model. But anyway, in a big corpus of information, if you want to find similar words which appear in the similar context of the word you're looking for. Let's say the word you're looking for is IMAX, name of the theater, IMAX. John went to IMAX theater, or nice new movies are being played in IMAX today. If you want to find what words co-occur with the words which are in the similar context of IMAX, that is, if you look at the word previous and one word after, I want to find what comes in the middle in other instances for the same first word and same third word. Yeah, you understand the concept? Similar? And let's see how long that takes for that to work. So I'm actually going to run this again on my Jupyter. Okay, it went through. So I'm using the corpus brown. Let me go back to show the. So I picked up the brown corpus, which is one of the corpus available, and I want to find what words typically come before and after. No, what are the words that come similar to women in terms of the context-wise, where they have the first word and the third word being very same or similar or same. Okay, let's see. Brown corpus, I think, is, I don't know, 60,000, 70,000 sentences or words thing. So it picks up, I think, in hardly a couple of seconds. There are a lot of other types of processing you can do. I'm only showing a couple because 4 hours you can't teach too much of everything of NLTK because there's so many exciting things in summarization, question answering. I want to even share in my second company, but first AI company, we developed a solution that processes documents to compare document and also rank documents. That's a generic sentence. But in the process, what we also did was we did a little bit of a question answering. If you feed a bunch of text to the computer, neural network, deep model, and then after that you ask a question, it will answer the question. But the question cannot be, the president of United States is Donald Trump, and then the question is, who is the president of United States? No, that's not the question. Then you can just use a regular pattern matching. The story is the following. Let's say Sally went to the kitchen, John went there too, it was bright morning, Sally said a hi too. And if your question is, Who did Sally say hi to? We all know the answer. But the model doesn't know. First, Sally is a human being, and there's another human being in the place. Model doesn't know where John is. Model knows where Sally is. Excuse me. Sally went to the kitchen, John went there too. So by doing a regular pattern matching, you cannot find the answer. So question answering is another interesting aspect, which I'll talk about that. So when we develop the model, there are a bunch of data sets available, but instead of taking the regular data sets, what I did was I took a massive Indian story. If you guys have heard of the story called Mahabharata. It's a massive online text available, maybe around, I don't know, a million, maybe 500,000 sentences. So we fed the model with that story, and then later on when you ask a question, it was giving answers, and the accuracy rate was 72%. That would be one of the use cases if you guys want to use the processing of the text. I'm only showing only a few, but there are so many other activities you can do. So that's why when you go home, I think you should work on that. Yeah. Yeah. Let's say you're in a healthcare situation. You want to find patients who have similar symptoms like David. Now, David has, let's say, 2 symptoms or 2 situations or 2 whatever. Let's say David has hypertension and, I don't know, headache. In a sentence about other patients, the word headache may not be the same word they use to refer to headache. There could be other words, number 1. Number 2, similar is the hypertension too. Number 2, the word just before the patient name, patient 1, patient 2, patient 3, and the word just after patient 1 may not be referring to headache or hypertension. When you run this type of, you have to do a little more processing. What I'm showing right now is just purely pick the first and the third word. But if you do a little bit of a rule engine, it's picking up words which are very similar to the context what you're looking for. So that's one use case where you want to find similar patients. You want to find similar situations or similar cities which has the same set of entertainment or attractions, what you're looking for. Or flights which are in the similar prices. If you're trying to take a flight from A to B, those are some situations where you have a bunch of text, you can do a similar, extract the information what you're looking for, maybe even get the sentence, and then do further rule engine to process and find the information. That's one couple of use cases I can think of. It is, yes. The example I just gave you about training a deep neural network on that my Mahabharata story, 72% accurate means 28% of the time it's giving a wrong answer. I'll give an example of machine translation which Google has come out with, I think 6 months ago. All my solutions which I'm going to be sharing are all papers, technical papers. Even some of the latest fantastic models are not 100% accurate. So when you are using NLP for non-regulated, non-life-threatening problems, it's easier because you can afford to have a little bit of inaccuracies. The biggest concern, and hence most investments by VC funds into healthcare, is because it's a life and death situation. You can't make an error, and hence making sure that the model picks the right answer for your question is a quest still going on. People have not figured out. I will give you another solution where in a translation, machine translation, language translation, to increase the accuracy, you can add a concept called language model, which is actually relatively new. And I will talk about that. That's why I said the implementation details, if your system is not working, if you're not able to install it, don't worry, you can go home and do it. But I want you guys to, when you leave today, leave with the concepts where you are absolutely sure what a sequence-to-sequence model is. When would you use that? Would you use an RNN versus LSTM? Why would you use an LSTM versus GRU? That concepts I want to clear today. When you guys go home, you can kickstart your learning quest on NLP. I've done a similar training in a different conference the other day, and it was 3.5 hours. And the title, I was trying to look for a funny title. I said 9 months of NLP in 4 hours. What I'm teaching today is actually, I took almost a year to learn and understand. And in 4 hours, you guys are ready, hopefully, to listen to whatever I'm speaking. Long time ago, I had a favorite boss in my company. He used to say, if I give you a message, for the message to be 100% understood, I need to repeat the message 7 times. So please sign up for 6 more times for this conference next time when you come, because to get the message completely. So it is actually lots and lots of concepts I'm going to be talking about. And because there are a variety of people in the audience, some are really good programmers, some people don't have a clue what NLP is, some people have an introductory information, some people are intermediate, they actually know some of stuff and they want to find out advanced techniques. I'm actually trying to cater to all of those, but I'm trying to, the underlying concept for every one of you is, what are some of the fundamental concepts that are the building blocks to construct an NLP-based solution, whether it's your healthcare solution or a transportation case, whatever it is you're trying to do, you will be able to, I think you will know at least 10-20% of that when you go home and start using that. So when you start reading up a few blogs, a few papers, you will be able to better understand. And also I have a stand on these papers. I'm sure you would have seen lots of papers, technical papers. I know you have a comment, I'll come to you. All the technical papers are written not to teach you. They're written to show how smart the author was or is. So you will not be able to learn from the papers, at least when you are in the beginner stage. When you are intermediate and advanced stage, yes, you can pick up the papers because there's lots and lots of math. I will be using some math today, but I'll try to not to use as much math because you guys all like math? Yeah? Okay, fantastic. If you guys like math, I'll tell you a math story. But before that, can you go to your question? Yeah. So when it picks up, it actually tells you the location where it's picking it from.
Visually, I mean, this is coming from the real case. When I give the answer for my customer, the customer immediately wants to go through all the places.
Yes.
So then it becomes like a application I have to like integrate with some other tool.
Yeah.
Elasticsearch.
You got to do some more programming on top to actually get to the links where it is, but it actually knows. I'm not showing that part. It knows where it's picked up from. Yeah, you got to write an additional program for that. Yeah. The question is, for the similar example, what I just showed, similar when I picked up instances where the word found similar instances, instance 1, instance 2, instance 3, and if it's picking up from 3 different documents, can I also link that document so that if I want to do further deep dive, can I find the links? Yes, it knows, but you need to do an extra programming to find out what the link is. Yes, it knows. Okay, you talked about mathematics, but before we go to the mathematics, what time do you guys want to take a break? If you want to take a break now and come back at 12:30, that's fine too, but I just want to know. Maybe, yeah, let's take a break, maybe another half an hour. Is that okay? Yeah, yeah. Okay, mathematics, you guys right, eh? And this is not NLP, so you can put your computers away and then I said, oh, thank God. Have you heard of a concept, mathematical concept called Monty Hall problem? Yeah? Okay, fantastic. Let's talk about that. If you do, people who have not heard of it, it's like a game show where you have 3 doors and you have a fantastic gift kept behind one door like a car, and one from the audience will be called and asked to pick a door number 1, 2, 3, and then everyone is clapping and it's all excited because if you pick the right door and if the car is right behind the door, you get that car. Yeah, it's so exciting. Have you seen that? So let's say there are 3 doors. You are the participant, each one of you. I want you to imagine each one of you are the participant, and the car on the other side is actually the Tesla, the best, recent, most Tesla. Okay? It's to make it exciting. And I am the organizer, and I ask you, okay, what's the door number you want to pick? And out of 1, 2, 3, you pick a door. Yeah? Let's say you pick door number 1. To make it more exciting for the audience, what the organizers do, the game shows, is they open one of the other 2 doors randomly, which does not have the car. Typically, they keep goats, and that's the multi-hall problem is actually goat, but it could be any other funny thing too, some cheap item. So let's say they open door number 2, and there is a goat behind door number 2. Now we have 2 doors to pick. You already picked one, which you can allow to change if you want to, and there's door number 3. You don't know which door has the car. Now, the organizer of the game says, okay, do you want to change your choice? Do you want to still stick with door number 1, or do you want to change to go to door number 3? If you are a mathematician, what is the recommendation? Someone said change, doesn't matter. No, just pick a door. I know it's a. You switch? Okay, fantastic. Anyone else? You keep number 1 or you switch to 3? Switch, 3, okay. Keep 1. Switch. Okay. The mathematical answer for this is it's always a better idea to switch. The probability of you winning becomes 66% if you play the game multiple times. It's of course a theoretical game because you'll be only given a chance once, so you don't know whether to switch and keep. But if you're a mathematician, because all mathematicians always think they can repeat the game multiple times, yeah, which is not the case all the time. But the probability of winning a car goes up to 66% if you switch, and remains 1/3, that is 20% or even 33% or even lesser if you keep what you already picked. I won't explain what it is. Go back and check online. But I wanted to tell you the story just because you guys said you like mathematics. But okay, so let's go back to our regular stuff, what we came to study. So there are other examples of similar, but I'm not going to show those. Okay. In English language, you have all the words, and each word communicates a message, and you want to extract the word, you want to find out the word, you can do a parts of speech tagging of the word, you want to do a named entity recognition, NER on it. But there are some words which don't actually give any meaning, like in, the, a, an, of. Sometimes they may give a meaning because it actually modifies a verb or noun or whatever, but many times they don't. Those are called stop words. Every NLP tool like NLTK, Core NLP, they actually have collected a bunch of stop words, and you can eliminate those from the text so that processing can be better. You can also modify what would be a stop word, what should not be a stop word, but this is an example of how to identify the stop words. I'll just show you what the stop words are. So let's go back and I will just show you what are the various stop words available. So I'm importing all the stop words, and then I'm going to actually, and these are stop words for English language. They have actually corpus for other languages too. Of course, the most frequently used language is. So these are some of the stop words which the model feels I don't know how to do this. Okay, you guys see, hope the font you can see. These are some of the stop words the model or the framework believes it's not going to help. And you can eliminate these stop words in one single stroke. And if you feel some of the words are useful, you can keep them, but you need to just go back to modify the dictionary of the stop words. Okay, let's get to you might have heard of something called sentiment analysis. Every company does sentiment analysis. Yeah? Yes? No? You know, when I first started teaching as a hobby long time ago, when I was still young, I wanted to ask a professor, how do I know that the audience are still engaged since they are listening to me? Oh, he says a simple thing. Just ask a couple of silly questions. Are you there? Are you listening to me? And if you feel an emphatic yes, then they're still engaged. If there is whatever and there's no response, maybe it's time for you to take a break. So let me ask the question again. Have you heard of sentiment analysis? Yes. Okay, fantastic. Okay. Which only means that we're going to take a break a little later, not now immediately. Sentiment analysis using text is a solved problem almost 2-3 years ago. If you are, let's say, a new car company or a product company like a phone company, and if you want to find out how the audience are feeling, you can get a product level feedback immediately, and that problem has been solved 2-3 years ago using NLP. But off late, I think it's more of the feature level feedback. Yes, I like the phone, but the screen is really bad, the resolution is fine, cameras really suck. If that's the feedback you're getting, you want to know immediately. But I'm going to show a product level feedback, and I want to show how simple, extremely simple, is to figure out sentiment. So I have a data set. So if you have downloaded my entire set of files I've given in GitHub, there is a .csv file called tweets. If you want to open it, you can open it and see. There are around 9,000 tweets in it. So I'm actually going to develop a model right in front of you. Actually, I've already written, I just need to run it. And it processes and identifies the sentiment of 3 sentences I've put in the file. I want you to see how simple it is to develop a sentiment analysis model. I want you to appreciate that the corpus, the data set, is such a small data set. It's 9,000 tweets. Half of them are positive tweets and half of them are negative tweets, so that the model can understand what's positive, what's negative, or no feedback. That is neutral. So 1/3, 1/3, 1/3. And also I want to see how sometimes model is intelligent or not intelligent, okay? So I'm actually going to open Python, and I'm actually using an older version of PyCharm. So what it does is it actually closes every time because I don't have a license. I'm actually going to open it again. So classifier.py, if you want to open it. And the interpreter I'm going to use is 3.6. And you can do anything else, but I think it works. It's 3, but not 2. Python 2, it may not work. So here is the 2 data points I want you to take away. Look at the number of lines of code. 24, including blanks and including my inference statements. This model is going to do a sentiment analysis of 9,000 tweets in a split second. And it will also identify what the sentiment is for this sentence. This is fantastic. iPhone not bad. iPhone cost too much. Okay? So let's see. Hopefully it runs without any complaints. There you go. The first one, it says positive emotion. Second, okay, let me push this up. I don't know whether I can increase the font size. Hopefully you guys can see the font at the bottom. iPhone not bad. no emotion toward brand or product. And number 3, iPhone costs too much, negative emotion. If you guys can, if you're able to run it on your laptop, change that text randomly whatever you want. A negative sounding, positive sounding, and see if it's smart enough to figure out. Oh, this is so fantastic if I had $1 million, because you're putting a sarcasm in it. Yeah? Sometimes people put a sarcasm, but they're using positive words. Oh my God, this is such a fantastic phone, only if I had $1 million, which means it's really a bad phone for the money they're charging. And put that sentence and see if it figures out or not. But remember, this indeed make mistakes too. The accuracy is not 100%. It does make mistake. And one of the primary reasons for that is the data set is very, very small, number 1. It's only 9,000 data set. But there's another interesting aspect for why this is not very accurate, and I want people to take a guess. If you can or cannot, then I'll tell you the right answer. There's one more data point why I think it's not as accurate as you can think. Let's say if you have 4 other sentences, 5 other sentences, I think sometimes it may not figure out. Yes, sir.
Yeah, okay. So I have tried to solve this problem. In one, I found out you can either give them a hot list of positive words and negative words that comes from professors that covered in Chicago. And another is that Python, they have a package recently became popular because they run actual survey and they made a tool which actually asks people and from that they figure out. And I think this must be doing statistically.
No, this is actually running a NLP model. The statistical models which were done a few years ago, those are not scalable anymore. So that's why I think the whole machine learning and AI, deep learning is getting really popular, because you don't have to use any of those non-scalable models anymore. This actually can scale fantastically. And so, but I'm only showing here just for 9,000 tweets as a classroom assignment. Anyway, going back to my second question on why the accuracy is low, can you guys predict anything? Yeah. I am not sure whether the sequence of the words it's actually figuring out. What it's figuring out is it's actually getting the overall sentiment of a sentence. Let's say if you say, this is a bad phone and this is a good phone. This is not bad phone and this is a bad phone. It will figure out not bad, negative, double negative is actually a positive. It will figure out, because if you have given enough data. It's not doing a pattern matching. It's not looking for a specific word. It's not statistical anymore. So I'm not sure if I understood your comment correctly. I don't think that's the answer. But
yeah, one more way you can do it, you can count each word.
No counting. There's no counting. This is not statistical anymore. This is deep learning, NLP. Any other comments why the data data is wrong? Open the Excel sheet. Sorry? Oh, okay. Well, sure. There are different models, especially 2-class classifiers. There are so many models available. Individual models sometimes may work. Some individual models may work well in some cases, and some other cases it may not. And people use an ensemble where they collect multiple models. Yes, sure. That's a possibility. Sorry, yeah, I didn't think about that. But there's another one which the answer which I'm looking for is not that. You had a comment, sir? No, that's what I said. If you use another model, let's say XGBoost or decision trees or whatever, you may have similar inaccuracies, but the inaccuracy could be somewhere else. It may not be 100% accurate. Where? Yes, that's it. Whenever you do a machine learning solution, the effort you spend in developing a solution should be only 20% of the effort. 80% of the effort, you got to understand the data. You got to go check the data. It's like you fall in love with the data. You got to keep looking at the data. Especially if you don't feel like sleeping in the night, you should keep looking at the data. In this case, if you open it and do a little bit of a permutation combination, you can do a little bit of ordering, you'll find, I don't know whether it's the negative sentiment or the positive sentiment, the number of tweets available for a negative sentiment or a positive sentiment, I think they're not enough. So the model is not becoming intelligent enough to figure out the negative sentiment. It may be intelligent enough to figure out the positive sentiment, because out of the 9,000 data set, even if you look at the percentage distribution of the data for each class, in this case the class being positive, negative, and neutral are the three different answers or three different classes, you should have enough amount of data, number one. You should have balanced amount of data too, for the model to become intelligent. And hence, if you are really interested in ML, I'll give you a problem statement. Maybe you guys should go back and think about this. Let's say you're a bank and you're trying to do a fraud detection, credit card transaction frauds, okay? Typically a bank, let's say you're a Citibank or a Wells Fargo or whatever, and if you have you may have almost, let's say, 1 billion transactions per month maybe, and the number of fraud transactions will be, let's say, maybe 100 or 1,000, let's say 10,000. But what's the proportion of this 10,000 in a billion? So 999,000,999,000, whatever, are all positive transactions, and you have a few negative transactions. And if you give all this 1 billion transaction information to the model becomes extremely intelligent to figure out what's a positive transaction and does not have enough information about a negative transaction. But here is a kicker. If you have such a unbalanced data set, you don't need a model. You just say, okay, I'm going to be the model. Every transaction is a fair transaction, because you'll be still 99.999% accurate, because 99.999 times the data is right. There's not a fraud transaction. How would you define a model in such a context? Think about that. That's not NLP, but just for the heck of it, I mentioned that. Yes? To go where? To go where? Mm-hmm. Yeah, I don't know the answer. Good question. It's counting the sentences which are positive and negative. I think I was answering about the count there was, I think it's not counting the words. Which, okay. Yeah. You may be right. You may be right. I'm wrong on this, but this may be the wrong example then. I'll take that back. Yeah, sorry for that. Okay, let's get back to okay. I'm going to start the real NLP deep learning models now. The fundamental building block of NLP is recurrent neural network, RNNs. RNN is a type of neural network which actually takes word one by one, processes it, updates something called a hidden vector, and the hidden vector actually is capturing the essence of the input so far. If you say, Sally went to the kitchen, John went there too, and after these 10, 15 words, you input into RNN, and if you look into the hidden state, it's of course a bunch of numbers, you can't actually make sense out of it, but this bunch of numbers, which is called hidden vector, capture the essence of the feed you have given till now. That is the most fundamental building block in deep networks in NLP, because you have a series of text coming in, unlike in statistical machine learning or in image processing, where you have one image that comes in which may not have a correlation to the next image coming in. Similarly, for statistical analysis, if you're doing an email campaign response, which I mentioned to you earlier, each user, each customer who responds to email campaign is so different from the other person. So you actually can imagine every customer is a random customer. But in this case, you have the first word, the second word, third word, many times. The previous word was dependent on the current word, and sometimes the future word may be dependent on the current word. So there is a lot of dependencies, and this is all temporal aspect. One comes the word after. So it actually starts from the left to right. The model starts looking at word number 1, word number 2, word number 3, word number 4. It starts assimilating and synthesizing and keeping the information internally. What is the meaning of synthesizing? How does it synthesize? What information it keeps? How much of information it keeps? All of those questions we'll answer. And this is, RNN was invented, I think, some few decades ago, but I think the application of RNNs are happening more prevalent in the recent past, last 4 or 5 years. But in NLP, the using RNNs to process it, and it started around 3-4 years ago, maybe 5 years ago, more of 3-4 years ago. And in the last 1 or 2 years, there are other variations of RNNs that have come, which we'll talk about. But at this point of time, I want you to take the message. So you have X is an input, which is actually a word. Y, U, V, W are matrices, which actually are processing information. But I'll talk about those details later because they're going to get changed later on. T, T minus 1, T plus 1, these are all time steps. That is, at every word when you input to the model, it actually, it's a time step. So you actually move from one time step to the other time step. And every time step, the RNN is updating its hidden state. Whenever you understand RNN, the most important factor I want you to take away is the hidden state. That is the most essential component of RNN, and we'll talk about that. And we'll talk about other variations of it. But RNN, that's what an RNN is. I remember I talked about Shakespeare's a novel. There's a gentleman by name Andrei Karpathy. He's an extremely smart guy, PhD from Stanford, and he's taught there. Right now, he's the head of ML in Tesla. There are 2 people I admire the most. A lot of other people too, but in terms of ML, machine learning, there are 2 people. In NLP, there's a gentleman by name Richard Socher. When you hear him or see him or meet him next time, tell him I said this, that he's like God in NLP. The amount of contributions he has done for NLP is just mind-boggling. And he right now works for Salesforce. Yeah, that's one gentleman in NLP. Similarly, in image processing, there was another guy, another god called Andrei Karpathy, and that's the guy I just now mentioned about. He's also, he's developed a model here where he trained a RNN, not RNN but LSTM, but I'll talk about that later. But let's say he trained an RNN with all the novels of Shakespeare. This is Shakespeare, right? In this case, yeah, Shakespeare. And after multiple amounts of training, and when he asked the model to start writing a new story, it actually started writing a story that sounds and looks similar to Shakespeare's stories. Of course, there's no plot in it. Maybe the intricate plots are missing, and sometimes it does give out some gibberish. But if you look into the commas, the periods, the length of a word, and length of a sentence, how many words you can have. Look at even words like alas, which seems to be like a Shakespearean language. And also, it identifies the names of the roles, and the names of the roles are in caps, whereas the sentences or the dialogues the roles are mentioning is not in caps. It is amazing in terms of how accurate the model figured out what how Shakespeare writes and starts writing it. Of course, the sentences may not make real sense, but this is a training he has done using RNNs, actually a variation of RNNs.
Yeah, I just wanted to share a real world application of this. Harry Potter writer, she wrote a non-Harry Potter novel without using her full name.
Mm-hmm.
And she never let anyone know that she wrote it. Some people, some journalists, by running this kind of model, they could figure out she's the one who wrote it.
Oh, okay, okay.
After they're doing it, they mistake it.
Yeah.
So
Today, sorry.
it could prove that it is her writing.
Sure, yeah. You can train a model to figure out who the author is. Yeah, absolutely. Today we'll be doing one exercise. It's called generative model, which actually generates text. I have a smaller model and a bigger model. I have trained both the models. The training of the model for the smaller one took almost 35, 40 hours. on my regular iMac, not GPU. The bigger model, it took almost 66 hours, I think, on my iMac again. Because the model is already trained, you don't have to train it anymore. I have given the weight, so I've given the model to you. You can run the file, it'll run the model, and it actually starts generating a text. In the small model, it generates just a sentence. You can see it comes, well, it's gibberish, but it actually comes closer to what a human being would be writing. And if for a bigger model, it actually generates 100 to 150 words a paragraph, and it sounds more like a human being's language. Of course, it still outputs some gibberish, and sometimes it repeats the words and stuff. Some of the problems, what you normally find in generative models, what you will find hands-on. But that's more of a 1.5 years, 2 years ago research, but you'll actually be able to do that development yourself. It's 9:47. Too early? Not to leave for the day, I'm just taking a break. Okay, wait, maybe another 10 minutes? Yeah? 10 minutes, okay. I appreciate the assertiveness in that. 10, that's it, okay. RNNs have a problem. If you feed word by word in a series, after some time, RNN starts forgetting slowly what was the first word, what was the second word, what was the third word. It starts forgetting. In other words, what's the capacity of RNN? Experts say somewhere between 8 to 10 words. After 8 to 10 words, it starts forgetting the first word slowly. The moment you put the 11th word, it would not remember what the first word was. So if you're using that model to, let's say, oh, let's do a language translation. I give you a sentence in English, and then I want you to do a French translation. And if you have a 15-word sentence, it will forget what the first few words were. And if those were influencing the words that came after, the entire translation will go for a toss. So people, that's called vanishing gradients or exploding gradients. That's the two different problems for RNNs. We won't talk about what the exploding and vanishing gradients are, but a new model that came out called LSTM, long short-term memory. This is a variation of RNN. It also takes inputs one after the other in the same sequence. It also has hidden state. It also has something called cell state, but you compute the hidden state using the cell state. So practically, you can ignore what cell state is. And in other words, to summarize, an LSTM, the most important output of an LSTM is the hidden state, like RNN2. But because of the upgrades this RNN went through, it can store information about more number of tokens, more number of words. And according to Chris Manning, the professor in Stanford, he says you should take a number 100. If the input is longer than 100, then LSTM also starts forgetting. But that's 10 times better than RNN. So LSTMs are a variation of RNN, which take inputs in a sequence, does lots of processing. There's a lot of mathematics right there. And if you want, I can explain that too. The way it does it, it identifies what information to store, identify how much information to store, and what information to forget or ignore. And hence, it keeps a part of the memory open so that it can take at least information worth 100 words. That's the logic. And I can explain the various gates. You have the input gate, forget gate, output gate. But for today's discussion on the brevity, I would say LSTM is a variation of RNN, which actually takes lots of words as an input in a series and updates its hidden state. And the hidden state captures the essence of the input till now. If you're using LSTM to do a language translation or a summarization or question answering, you can use the hidden state to ask questions or to summarize or do a language translation because it captures at least 100 words worth of information. You had a question, sir? Yeah.
I was just curious about this 100 words. So I've checked Google, the latest translate, and it does it. It basically can't do gender understanding languages that have gender, even if it's clear from the sentence before. So I just kind of wonder where that number came from, because that doesn't seem correct.
There is a video of Chris Manning teaching the NLP course in Stanford, online YouTube video, and there's exactly this question asked to him, on how many words LSTM will. He said, for your mathematical and practical applications, take the word 100, but if, let's say, if the language is full of domain-specific words, and if it's too much of specific and loaded words, it may forget information faster. But he says take a number 100, and that's what I'm saying. If you, let's say if you're working for a healthcare or any other startup trying to develop a solution to do a language translation, anything longer than 100, you are sure the inaccuracies will go up. That is, the model will start giving wrong answers. So if you stick to, let's say, 50, the probability of the accuracy being higher just because it remembers is higher. So it remembers all the words, and hence, if you have any inaccuracies in the model, that's not because of the length of the input, it may be some other reason. Yeah, the sliding window, it's only when you're doing the input for training purposes. But if you have, let's say, a training window of, let's say, 5 words, and if you actually do lots of 5-word combinations, that's fine. It takes 20 such iterations and still remembers all the information. After that, it starts forgetting, so you need to actually do something about that to see how to keep that information loaded somewhere. So you actually can do updates of your weights and store some other way of doing it. But that's no. Window size cannot be more than 100 though, by the way. Okay, I'll stop here. That's LSTM. If you have any quick questions, I'll take the questions, and then otherwise we'll break. I don't know, Janling, what's the duration of the break? It'll come back in 10 minutes? Yeah, I think there's coffee and restroom break if you have any questions. And then we'll start with a yoga exercise. Okay, thank you guys. You cannot do without an LTK. But remember, I just downloaded it in front of you on my computer. It just took 2 seconds. NLTK, everything. I just downloaded everything. So I don't know how fast, but I am using the same Wi-Fi too. Is it? But mine took, I was just doing right in front of you.
Yeah, but all the students are hitting the same file at the same time. There are, what, 500 students?
Yeah, but I'm also like a student trying to download, so I don't know why it took so long time. I took only 2 seconds actually.
But I wonder if there's some buffer that you're... So it picks up characters
words are four characters, 5 characters long. Sometimes after a last comma comes, a period comes, the caps come sometimes, lowercase, uppercase. It knows all of that. Okay, can we start? NLP is trying to solve so many problems which were thought to be almost impossible. Sometimes you just could not imagine that you can solve this problem too. Even though you had so much of data, there was not enough models available, computing power available, but nowadays you can solve a lot. But talking about impossibility, I want to talk about what's impossible, okay? I'm sure you've heard of something called yoga? Yes? Okay. After the break, at least, you should be able to say yes a little more loudly. So one of the best things, there's so many exercises in yoga people do which actually keeps you really fit. I personally believe of all the yoga exercises, breathing exercises are a lot more important. But I'm sure some people may disagree. But let's talk about breathing exercises, okay? Indulge me. I want you to take a deep breath and do exhalation. You can close your eyes if you want to, or you can keep your eyes open. Normally, people close their eyes, but remember, the exhalation has to be longer than inhalation. Okay? Let's do it. Take care. Okay, you guys are done? Now tell me how long it took for you to breathe in and how long it took for you to breathe out. How many seconds? Few seconds, like 5 seconds, 10 seconds maybe in, and another 5, 10 seconds, or 20, maybe 15 seconds out. Now my question number one, can you breathe in and breathe out simultaneously? Sorry? Oh, okay, yeah, okay. You know, there is a fantastic English word called stealing my thunder. That's, that's exactly what but anyway, I will still get the message through a different way. I have a different story for that. If you have to play a musical instrument, almost the same thing but slightly, especially a flute or a saxophone, and if you want to hold a note, yeah, you blow it and continuously blow and hold a note. How long can you hold it? Like, ooh, how long can you actually do that with a wind instrument? 10 seconds, 15 seconds, 20 seconds. If I say someone actually can do for 45 minutes, can you believe that? Yes? Okay, yeah. There's a famous saxophonist called Kenny G who has done it, and also Australian Aborigines, actually, they do something called continuous breathing, where you can actually breathe in and breathe out simultaneously, but slightly modified, and hence you can actually play a musical instrument for 45 minutes. Actually, there's a YouTube video. It's not for 45 minutes, it just shows for 4 or 5 minutes, but he could do it for 45 minutes. The only thing is no one is going to watch 45 minutes of the video, so it's 4 or 5 minutes. So you should give a search for Kenny G on YouTube, you'll see that. The point I'm trying to make is the problems that may look impossible not always are impossible. Some are still impossible, I guess. How to live longer than 100 years, or maybe how not to die could be another problem which I think sounds impossible at this point of time. But there are a lot of problems machine learning is solving, which thought to be, I think, even 2 or 3 years ago, almost impossible, and people are trying to figure out. Before I get back into this, I want to clarify, a couple of people asked me the question about the 100-word limit thing. When you do more than 100 words, you have to let the model to assimilate the information. It does a back propagation and then assimilates the information. Now it's ready for another set of inputs. So in other words, while training, it can take millions of words in, but at a gaps of 100 words, and then it assimilates and then goes further. But while inference, let's say if you have a language model or translation model you trained, and you have used a parallel corpora of 1 million sentences in the source language and 1 million sentences in the target language, you train the model on these 1 million sentences, and now you are using it for production purposes. And during production, let's say, for example, you have a Google Translator app on your iPhone maybe, and when you start using it, it waits for you to finish the sentence and then translates. But if you speak for 15 minutes or 1 hour, it's not going to translate the whole 1 hour thing. It only catches for the last 20 seconds, 15 seconds, and then translates it. Okay. Now this is another most fundamental building block. You will see this word sequence to sequence, sec to sec, but sequence to sequence is the model. In NLP for sure, for many, many applications, but you will see this even in some image processing and audio processing too, but beyond the scope of today's presentation. Sequence to sequence model is nothing else but an extremely simple LSTM or RNN taking a few words in a sequence, and after the input sequence is done, it starts doing an output sequence. So the input is a sequence for the model, and output is a sequence too. Let's take an example. If you're doing a language translation, you give an input sentence in the source language, and the model is supposed to give the output in a target language. So in this case, if A, B, C, and a special token called end of sentence, EOS, is my input, and typically end of statement or a special token for the model is to alert the model that, okay, I've done my job, now do your job, type of alert, and then the model starts outputting. So at time step T1, input is A, and then time step T2 is B, and T3 is C, and at every step, the horizontal arrow you see going from the first box to the second box, that's the hidden state. The hidden state gets updated based on every input and goes to the next step. And the hidden state is transferred to the next step, and based on the new input coming in at that time step, the hidden states get further modified and keeps on going. And after the input C and the hidden state, whatever that comes out, goes to the next box, when the model encounters end of statement, a token or any special token, it updates its hidden state. Now it's ready to do its task. And if the model the training you have done is for translation, it starts outputting W, X, Y, Z, and end of statement, end of sentence token. Now, it keeps on outputting a character by character or word by word, and I'll talk about variations of characters and words in my models. But that's a simple sequence to sequence model. You give an input sequence called A, B, C, end of sentence, and then you get a sequence called X, Y, Z, W, X, Y, Z, end of sentence sequence. That's a sequence to sequence model, and it's the same RNN which actually is taking inputs, and then eventually it does the outputs. That's the essence of a sequence to sequence model, and at a very fundamental level. This was the first model suggested, I think, 2014. Later on, some people said, okay, to improve the learning capability of the model, when it starts outputting W after the first end of sentence, you have the W coming out. Is there a laser pointer I can show, we can use?
I bet there's a cursor on your computer.
I want to actually be facing the people and looking at the people, not into my monitor, that's why. So when you have the first output W, during training, this is the important detail. During training, let's say if W is not the right answer, yeah, its model is learning. If it's not the right answer, you tell the model what the right answer should have been at that stage, but you input the right answer in the next time step. So I can see that side too, but I'm actually seeing this side. the end of sentence outputs, okay, fantastic, thank you, sir. Hope you guys can see it too. I know, I'll try to see it from that side. So you have the end of sentence coming in, and you have the hidden state coming in, and the final hidden state gets, this final hidden state of the input sequence is processed, and because you have an end of sentence token coming in, the model thinks, okay, now it's time for me to give an output. It gives an output W. But what if the output W is not the right answer, or let's say if this is W prime, and if W is the right answer, you give an input, the right answer called W at the next time step. And remember, the horizontal arrow is your hidden state. The hidden state is constantly getting updated, even when it's taking inputs and even when it's giving outputs. So it's constantly updated. And the hidden state at this stage, let me show from this side. The hidden state at this stage the model knows that I have taken the inputs A, B, C and end of state sentence token, and I have also outputted W as my first output. That's what the essence of hidden state at this arrow is. And then when it goes to this arrow, the model knows what my inputs are and what my outputs are till my time. So it actually remembers every time steps what it has done. But going back earlier, as I said, sequence to sequence model, you give a series of inputs and then it does series of outputs. To improve the accuracy of the model, people figured out if you give the correct inputs at every stage, especially during training, the model will know, oh, sorry, I made a mistake, but this is the right answer. Okay, I'll remember that, and keeps on going. And if you repeat this maybe 1,000,000 times, the model knows what the right output should be based on my input during inference. So when you have trained the model, and if it's ready for you for production purposes, and if you're using it, and you give the input and it starts outputting. But the difference between training time versus inference time is, inference time you don't have a right answer. You just don't know what the right answer is. You just have to believe what the model is telling you is the right answer. Because training is done, model is already done. You can do a retraining later on. But so this picturization is during training how a model works, because you're actually getting the right answers. So that was stage 2 or improvement 2. Improvement 3, some people said, you know what? Even during inference, I actually can give inputs, the same outputs as inputs to the model, because the model, even though it has just now outputted W, I'm actually going to give input W as a W in the next stage, because the model can actually better understand what it has done, because it's a little more recent information, even though it's just one time step away. When it does an output W, let's say that is the right answer or the wrong answer. So it has an output. But you know what the right answer is. Loss function. So when you tell what the right answer is, it should have been W prime and not W. So it actually computes a loss function. And because you do a loss computation based on a mini batch, it accumulates all the losses, and when you're done with the mini batch, you go back and update your weights based on the losses. And then now it starts taking the next set of inputs. Yes, yeah, the loss function. So it actually computing the loss function based on the input. So I'll come to the mathematics also, but if you look into fundamentally what you're doing is on a non-mathematical explanation is you have the model outputting some things, and if it's not the right thing, you tell the model what the right thing is, model understands, and then keeps on understanding and improving and start doing it. But in a pure NLP mathematical model is after you give an input, model does some output. If that is a wrong output, you tell the model that's wrong. It it does something called a back propagation. It updates its weights to reflect what was its wrong answer and how wrong it was compared to the right answer. It computes the loss. It is a loss function. Every such training model will have loss functions, and we may or may not talk about loss functions. But let's say there is a loss function for this. It understands what was the right answer, what was its wrong answer, computes the difference between the two, and goes back and updates its weights. And it is now a little more intelligent to make a right prediction. And if you repeat this process maybe 1 million times or 2 million times, it actually becomes more and more intelligent and then makes more and more accurate predictions when you start using it for production purposes. So one question in this case is, can we have a 10 million or 20 million if we can have more such data to make it even 100% accurate? May or may not be. I don't know the answer because no one actually found a data set of 10 million, 20 million, maybe a billion numbers. Right now, I think people are in NLP areas, you can create data sets for maybe 1 million instances. I've seen some cases, but 200,000, 300,000 data sets, it's 200,000, 300,000 data points data set is what people can find, and models are responding accordingly. The more data, yes, you can find. There is a research which also says sometimes more data is not going to help, but there's no controlled study or a conclusive study to prove whether more data is going to be helpful or not. But at this point of time, the common accepted belief in NLP world or ML world is more data is better. You had a question? Yeah, go ahead.
I mean,
Okay.
So
the question is, how
checking
do you know
that
the right
problem.
answer? Yeah. So let's say if you're doing a language translation model. When you're training a new model to do a translation from a source language to a target language, you got to have a sentence in source language and a complementary solution, a sentence in the target language. So you have 1 million sentences, one supporting the translated sentence. And hence, you know what the right answer is. That is a human curated, human validated data set is there which actually shows that you know what the right answer is. And you're telling the model what the right answer is. So yes, you need to have the right answers first yourself. Yeah, did I answer your question correctly? Yeah, that was your question?
I said going in is you don't know, it's random. So the right answer you might not know, right? So that's the part that I'm confused.
Yeah, so let me explain again.
Yeah.
So when you're training, you have for a language translation, you have a parallel corpora from English to French. You're training a model which will translate English to French. But you need to have 10 sentences in English, and for each of the sentence in English, you need to have a translated French sentence. So instead of 10, you actually need to have 1 million. So when you give an input as an English sentence, and then it thinks, oh, let's say, I am going to the movie. That's the English sentence. And if you're doing a French, I don't know how to speak French, but let's say it starts saying something like, the moon is bigger today. If that's the translation it thinks in French for this sentence, I'm going to the movies, you say, no, that's wrong. The right sentence is whatever is the translation of French. So that's where the right and wrong is. So there should be a data set provided by the human beings to have it. Okay, let's come back to sequence to sequence. So, yes, sir. Okay. That is the current research going on because it's so sequential, it takes so much time because it's computerly expensive. Every word you're giving an input, let's say, people have figured out how to convert a character and a word into a vector, into a single number, large, gigantic number, and you can input that. There is research for paragraph vectors, document vectors, people have done, so you actually can convert the entire document into one gigantic number and you can give that. I have not seen enough research on paragraph vectors, sentence vectors, and document vectors. I have seen lots of research on character level vectors and word level vectors. So even today, many of the papers when they publish for any NLP research, you have the inputs of text going in as a character or as a word. sentence and paragraphs and documents, I have not seen enough papers. There are a few papers, but I have not seen. I will talk about when I say input A, input B, input C. What do you mean by input A? Is it just a character called A? I'm going to talk about it. It's not character A, it's a number. And how do I convert a character or a word into a number? That will be vectorization. I'll talk about that in a minute. But I want to conceptually explain how a sequence-to-sequence model works. Sequence model takes inputs in a sequence as a word or a character at this point of time. Yes, sir.
Yeah, I'm not very familiar with this thing, but will it be useful in understanding what to vector?
Yes, I'll have a slide on that. Let me, hold on to the thought. I'll come back to it. You're talking about the mathematical equation or just the picture still? I'll come to that. I have not come to that yet. Yeah. But I'm just right now only focusing on this bit. I'll come to the mathematics in a minute. Yes. So conceptually, that's a model, a sequence to sequence. It takes an input. To represent the same thing in a mathematic way, the probability of y1 to yt, y1 to yt are the outputs of the model. The probability of these being the right answers given the inputs x1 to xt, because that's the whole concept you're trying to see, you're trying to predict the outputs based on the inputs. So the probability of outputs given the inputs being high can be mathematically shown as the probability of yt, that is the output at any timestamp t. So let's say output at this timestamp or at this timestamp, at this timestamp. So mathematically, if you generalize it, the probability of yt is dependent on a few factors. And what are they? The factors are, one is the previously outputted outputs till now. Let's say if the probability of an output of z is dependent on what were the outputs till now and what was the input context vector. So the input context vector is the v. So you have the hidden vector or a context vector. People normally use interchangeably. Some papers I've seen using context vector, hidden vector, but if you want to, a lot of people seems to be using nowadays hidden state, so you can use a hidden state. The output at any point of time is a function of what was the input hidden vector that came when the inputs were being given, plus all the outputs till now. That's what it is. So let me show the same thing from on this side for people who could not see. So the probability of outputs y1 to yt is dependent on the inputs, which can be shown mathematically is the product of the probability of each word at time step yt, which is dependent on the hidden state that came in after the input and all the outputs till time t minus 1. Yes, sir. Okay. Yeah, okay. So in this model, the reason I smiled is actually I'm going to come to that slide, the point. In this sequence-to-sequence model, in one of the most fundamental sequence-to-sequence, people felt that after you give all the inputs what it needs and the hidden state which gets constantly updated, the last hidden state would capture the essence of the entire input. So I take one hidden state, which is the final hidden state of the input sequence. So the hidden state after I inputted end of sentence token here, that hidden state I take, that hidden state is coming in here, and I start outputting the first word. And it was accurate enough, but people came out with modifications to that, and I'll talk about those modifications. So the comment I think he mentioned, he said, why the hidden state v is a constant, why not you pick hidden state at every time step? And that's a suggestion people made too. So this is almost the same example and in a slightly different way. This is an upgrade from sequence to sequence. People said, hang on, in the sequence to sequence model, it's the same model which actually is reading the inputs and giving the outputs. In other words, it's actually sharing weights. They said, this is not going to work because the model is not that accurate if I share the weights of the input sequence and the output sequence. So they said we are going to have two different RNNs. One will take all the inputs and at the end produce a hidden state. I'll have another RNN which will take the hidden state of the previous RNN and starts outputting. So they called it as encoder and decoder, which is exactly the sequence-to-sequence model, but instead of sharing the weights, they use, instead of having the same RNN, same LSTM being used, they use two different LSTMs. So you have one LSTM which will only take the inputs and process it and gets the, becomes mature and intelligent and gives the final hidden state, which is this blue, the first blue arrow, and it then goes the new RNN, which is actually is called a decoder. So encoder decoder as a concept, which is more of a breaking of a sequence-to-sequence model, and the only difference is you have two different RNNs, hence you're not sharing any weights, and consequently the model starts becoming more intelligent, but the rest of the functionality remain the same. You have a sequence of inputs coming in, and at every sequence you have the hidden state getting updated, and the last hidden state, which essentially captures the essence of the input, is given to the new RNN, and the new RNN starts using that to output. And at every time step again, the hidden state gets modified. It's, see, what is an RNN? RNN is nothing but as a big matrix of numbers which is randomly initialized to start with. Many times it could be zeros or it could be ones or just randomly initialized. And every time you give an input to the model and the model makes a prediction and the prediction is wrong, then you tell, no, that's wrong, the right answer is this. It does a loss calculation, and you think, with my initial matrix numbers, I got a wrong answer, but the wrong was so wrong, oh my God, I need to go back and change my matrix numbers. So it's called backpropagation, where you compute the loss and then go back and update your numbers. So I'm actually trying to make it as non-NLP as possible so that it's easy to understand. So you're actually having that weights which are getting modified. If you're using the same LSTM to take the inputs and eventually start even outputting, people felt it was not as accurate, so they felt it was more accurate to use two different RNNs, where don't care for the weights of the encoder. Once it's done, just I want only your hidden state, and I have a new RNN with a new initialized set of weights. I'm going to use that to start making predictions, and hence, it becomes more intelligent in the process.
So in general, what's the ratio of the size of the context vector to the word vector? Is y1, if y1 is a vector of size n, is the context vector exponentially larger, or other way around?
The question is, I'm trying to understand the question too. The word vector dimensionality and the context vector dimensionality, are they comparable? Is that your question?
Well, which one stores, you'd imagine that the context vector would be larger because it stores more information. You'd imagine that the context vector would be larger because it stores more information. So I'm asking, is it usually is the hidden state larger, or is the output word vector larger usually?
Okay. So you're actually confusing between two different concepts. A word vector is a vector that just represents a single word. There are multiple ways of creating a word. I'll actually, I think a couple of slides later, I'll be talking about how to create word vectors, the different types of word vectors. So a word vector captures the essence of just that word. Whereas a context vector, context vector, hidden state, interchangeably used, the hidden state is an understanding of all the inputs that have come in. You can decide what the dimensionality of your word vector can be, and you can also decide what should be the dimensions of your model too, which is in this case the RNN. And higher the dimensions and the deep, how many layers of network you have, all of those hyperparameters you can do a permutation combination to understand which ones work better, but conceptually, word vector is just representing just that particular word. And the word vector, let's say I'm going to the movie. The word I am going to the movies, all of these words can be represented by different vectors, all will have the same dimensionality. Let's say if you want a dimensional of 200 dimensions vector, you will create a vector for I which is 200 dimensions, but it's a unique number compared to am, compared to going to. But the hidden state is a matrix which is a different dimensionality, which you can decide what you want it to be. It's a matrix, and it's constantly getting updated based on the loss and backpropagation and stuff. So that's what I think I understood from your question. They're not comparable. But if you can hold on to the question about word vectors, I'll come to the word vectors, and maybe if you still have the question, we can talk about that. Yes, sir.
So the completeness or richness of your training
Okay.
set.
The question is, how do you know the quality of a data set is really of good quality? Sometimes you have a bad data set, and hence, yeah, you could be training on a bad data set. Yeah, that's the question, right? Yeah. That is a major question, and if you remember correctly, I mentioned earlier in your project, if you do any ML project, 20% is only what you do in developing a model, 80% is just making a pre-processing and making sure the data is accurate. One of the biggest problems today is actually lack of good quality data. And when I say lack of good quality data is sometimes the data is missing, inaccurate, incomplete, erroneous, in different format, different units. There's so many problems in a data, and especially in companies like, let's say, IBM or Apple or Google, the data is stored in so many different data sets and different locations, different databases, different formats, and putting the data together and trying to make sense is a bigger problem. That's number one. Number two, when you're doing an image processing or a language translation or any of such problems, having human-created data sets is so difficult, so expensive. Some universities have invested, some companies have invested money to hire people to create data sets, but there are not enough data sets available. So, for example, in image processing, there's something called MNIST or CFAR10. There's some data sets available, but that's the same data sets being used by every company or every research project to check how good the model is, but there's no other type of data sets available. There are companies which are available, so that's another good idea. If you want to start a company and want to make a lot of money, instead of doing ML projects, try to do data creation, data set creation. There's a lot of companies making huge amount of money on creating data sets. Yes, sir.
Not worried about the quality of data. Assume you have perfect quality. I'm worried about structurally. So when you want to train your model, you know you see what I mean?
Yeah,
so,
yeah.
So whether you initially give it in individual words, then more complicated sentences, et cetera, to help it train or learn better or be trained better.
When you say complicated sentence, I think I don't understand, but right now the data sets are, no, it's okay. Data sets, I think they are having different types of inputs. Let's say if you're trying to do, let me take an example of language translation. There's certain corpora available for English to French, English to German translations. When they do that, what they do is they actually pick random sentences from different sources of books and papers and online stuff, and then identify human beings who actually can translate those sentences into a foreign language, whatever language it is. And when they pick the sentences, they do pick different types of sentences, different structure, different complexity, different length, different unknown words or difficult words and all of that stuff. Yeah, they do. But that's where, when I say quality of data set, that's what I meant. It could be incomplete, not appropriate, erroneous, not complicated, it does not reflect the real world. There could be so many situations. But that's where the whole problem is. Getting the good quality data set is a problem. No, I don't think so. Right now, just the fact that a lot of research companies are using the data set for running their models itself could be a sign that, okay, this could be a good quality data set. The fact that it has missing data, incomplete data, erroneous information also goes a long way in having a more generalized model, because you can't have a perfect real life situation and data set all the time. So sometimes it's data erroneous, missing data is fine. The measures to see whether the model is doing fine or not, especially in textual context. Let's say if you have a translation model and it does a translation. Let's say I create a machine translation from English to French and you create another model which is doing English to French. How do you know my model is doing a better job than your model? Because every sentence is different, every paragraph you're translating is different. So there are some metrics called BLEU scores, BLEU scores, and there's another score called ROUGE, ROUGE scores. One shows the precision, one shows the recall numbers, but mathematically it's difficult to compute how my translation is better than your translation, because you can translate a sentence in another language in different ways, and hence it's an NLP. That's a big problem. It's an issue. I'm checking my time just to make sure I do cover. Yes.
Hello. Whenever you have some time during this training, could you please give us some best practices about how is there any best practice for handling missing data, or like specific, like data cleaning specific to NLP domain? I mean, not immediately, but whenever you think you can plug it in, I think that's something we are having a lot of trouble on that.
Okay, I'll try to say a few things, but again, what can be used to clean up data is more of specific about what the data is and what the purpose is, what type of objective you're trying to solve. So it's going to be a little more case sensitive, but I'll try to see if I can. Okay, coming back to the encoder and decoder, I just want to show you one more time. So hidden state is mentioned as HT, is a function of XT, which is so hidden state at time step T is a function of the input at time step T and the previous hidden state. So every time a new hidden state gets created based on the previous hidden state and the current input. And you have an output vector, which is sometimes the context vector, which is actually a function of all the hidden states. This is where I think goes back to your question. Sorry, the gentleman sitting there in the front. Goes back to in the context vector, see here, if you are actually using all the hidden states instead of just taking the last hidden state. Some experiments have taken the last hidden state and thinking that it's going to be, it captures all the information. Some other experiments have taken all the hidden states at every time step and do a function on it, and then have a new hidden state which is being used. It is called context vector, but that's a different experiment. Different experiments people have done, but mathematically that's how you show in an encoder. Let's show decoder from here. You guys, I think, may enjoy the decoder here. The probability of y1 to yt at time step t is dependent on all the previous outputs and the context vector, which can be shown as the probability of yt at any point of time t is dependent on the previous output, the hidden state of decoder at time step t, and the static hidden state or the context vector of the encoder. Now comes the situation where you have the input context vector of the encoder coming in, and you also have the hidden state of the decoder at every time step, and the previous word which is output are all factors that go into predicting the next output. Okay, so instead of just only sticking to the hidden state of encoder, now I'm using too many words, I want you to please listen to this. Instead of focusing on the hidden state of encoder at one time, as I showed in the previous slide, there are some models which say, instead of just focusing only one time, can I go back and look at what was the hidden state of the encoder at every time step? So I want to know, tell me once again what the hidden state was. Tell me once again at every time I'm outputting. So this is called encoder decoder with a peek. So it's actually taking a peek at what was the hidden state of encoder. That's another variation which has come. So you have the sequence-to-sequence model, which is the same RNN being used, then came encoder-decoder, then came encoder-decoder with a peak, and then came a new technique called attention. The intuition for attention is, when you're doing a summarization of text, when you have a bunch of text, you read the text, and then you're trying to summarize the text. Or when you take a bunch of text and you're doing a language translation. What would normally human beings do? After reading the entire sentence or paragraph, when you're doing the output, once in a while you want to go back and check maybe one or two words or one or two phrases that is of more important for you at that time step, because you're outputting word number 7, but for word number 7, you want to go look at word number 8, 23, 44 of input, because those words are modifying my output number 7. So model is getting a chance to go back and look at what was the input. And instead of looking at the real input, it actually goes and looks at the hidden state at those words. So if each word is a time step, so instead of 7th word and 10th word and 25th word, at time step 7, time step 14 and whatever, 24, look at the hidden states. I want to look at those hidden states and predict my YT at this time. That is attention. So it's instead of only looking at the last hidden state of the encoder, I want to go back and look at specifically a few hidden states of the encoder when I'm doing my decoding activity. Okay, that's a mathematical implementation right there. There's another way of showing attention, which is exactly the same again. You have an encoder. In this case, you have a multi-layer encoder and with also skip-level connections. This is from this paper. Where's the paper? Yeah, paper is right here. You guys can check. All my details are from paper, so you can actually go back and check. When I share the slides, you will also have the references to the papers. And you have, this is the decoder happening here, and the decoder at every time step, it actually goes back and looks at the hidden state, the output hidden state of the encoder, but also it goes back and checks what were the hidden states of various, the hidden states of encoder at various time steps. Okay, we talked about so much of hidden states, encoders, decoders, having a peak, attention. This all looks extremely complicated programming activity. It's not. I think this is Keras model. Yeah, Keras. Almost every framework has some way of implementation of it. All that you have to do is, for example, this is a very simple sequence-to-sequence implementation. And in a sequence-to-sequence with the peak, I think you just have to set the, I can't see from, yeah. Peak is equal to true, I think. Yeah, peak is equal to true. That's it. The model will look at when you say peak is equal to true, it constantly goes back and checks the hidden state of encoder for every time step of decoding, and with just that one. So the programming aspect is very, very trivial. So if you guys are not able to do the hands-on today, right now, in the morning, when we started in the morning, or if you're not able to, if you think it's too complicated, that is becoming more and more trivial. But it's the concepts people, I think, need to be aware of. Let's talk about word vectors, so how to create vectors out of the words. Before I get into words, let me define a concept called vocabulary. If you, for any NLP cases, you have an input corpora or a text that goes in, you need to identify how many are unique words in my input corpora. That's called vocab, the vocabulary. And the vocabulary size is an extremely important factor at this point of time, because for encoding purposes, you need to have a set of vocabulary where the encoder takes those words from the vocab, and while decoding, the RNN or LSTM also needs to pick from words from a vocab. They can be two different vocabs, different set of vocabs for encoder and decoder, but the size of a vocab at this point of time, I have not seen more between, actually I've seen between 50 to 80,000 words. I have not seen enough experiments where the vocab size is more than that. What does that mean? It means when you're doing a language translation from English to French, that the different types of word the model can understand is those 50,000 or 80,000 words. If you give a new word, it doesn't have a clue what it is. And it puts out something called UNK, unknown, U-N-K, because it has not been trained on this new word which you are giving during inference, because while training, it's not in the vocab, and hence it doesn't know what the word is. Similarly, when it's doing decoding, doing training, it picks up the words from its own vocab. But if it encounters some strange word, and it does not know what the meaning of that, and if it's not there in its decoder vocab, it again outputs an UNK there, because it does not know. So you need to have a vocab. Why can't we have a million as a word? Computationally expensive, because you need to have that amount of data set to which you are using a million tokens and as inputs and another million tokens as output, which is not possible. So 50 to 80,000 is what it is. So with that definition of vocab, one-hot vectors is the most common one. Many times this works even better than word-to-vec, but a lot of people actually believe word-to-vec also work. I do have an experience of training my question answering model using all the three models, one-hot vector, word-to-vec, and glove. I found the model accuracy was the highest, 72% when I was doing one-hot vectors. But a lot of people feel one-hot vector does not capture a few essential information. But let me first define what a one-hot vector is. Let's say your vocab is 10 words. I am going to the movies. If that's your entire corpora, so you have a 7-word vocabulary, okay? Let's say you have a 7-word vocabulary. You create a vector of 7 dimensions, that is 7 zeros, but the vector for I will have a 1 in the first place. So that will be 1, 0, 0, 0, 0, 0, 0. So if you have 7 words, and if you're giving a vector for word I, and I is number 1 position in your vocab, you put a 1 in place of 0 for that vector, and that becomes a unique identifier for that word, and same is the case for the rest of the words. So one hot vector is, or 1 of k, one hot vector is the vector with lots of, or actually everything zeros except 1 at that place where the word is in the vocabulary. Okay, that's a one hot vector. But the problem in that is, I am going to the movies, movies I am going, I am the to movies the going. If you rearrange the words in any fashion, the word one hot vectors will almost have a similar the vectors, and it's not capturing the sequence information, which is the biggest drawback in one hot vectors. But I've seen one hot vectors working very effectively too. So you may want to be aware of how one hot vectors are created. Another way of creating word vectors is co-occurrence vectors. If the word I am, if the word am comes almost many times next to I, not next to movies, am movies, the word am does not appear next to movies, but mostly occurs next to I, you want to capture that message, that information. So it's called co-occurrence metrics. Is you want to identify, you want to give vectors to words, similar vectors to words which occur very close to each other. So there's a style of doing it where if this is the entire vocabulary, I enjoy flying, I like NLP, I like deep learning, you actually make a table, you find for each of the word how many times the word occurs in next to it, and then you can put the numbers. I don't want to get into the details. I have not seen people using co-occurrence vectors. Actually, I have not seen ever in the last 2-3 years papers people using it. But I just wanted to share that method of doing it. Word-to-vec is the most popular, and there's another method called glove, which I don't think we'll be talking, but word-to-vec is another way of doing it. It does actually do it in 2 different ways. One is continuous bag of words. There's another called skipgram. Continuous bag of word is you train you create a vector based on large amount of corpora where you pick a word and you predict the probability of 2 words before and 2 words after using continuous bag of words. That's a skipgram. Continuous bag of words, you actually identify 4 words, 2 words before and 2 words after, and then you predict what the word is. But you don't need to do any of the math. There is in the many other frameworks like TensorFlow, for example, just a one-line code where you want to create word vectors for a bunch of corpora you have. You can just run a couple of lines code and then you can create word vectors there. So let's create word vectors. Okay, I need to restart it again, I guess.
Excuse me. This side.
This side.
On your left.
On my left, okay? Okay,
here.
yeah, there you go.
Okay. I was just confused by the fact, as you mentioned, that glove is another representation of word vectors, or is just a pre-trained model that you can use out of box?
Glove, when you expand it, it's actually called global vectors. That's another way of doing vectors, identifying vectors. Word2vec, glove is actually invented by Google. That's a way of creating vectors. And Word2vec is another way of creating vectors.
Is there a fundamental difference in how they create it?
As far as I know, I think Word2vec using continuous backup words and glove is using skipgram, but I'm not very sure.
I think a glove is a content-based model, and Word2vec is a predictive-based model.
Word2vec is a very good model. Yes, I agree. What was the first one you said?
The glove is a count-based model. It's a concurrency matrix. And the Word2vec use like skipgram and those two models.
Yeah.
So they are different. Essentially, they're
You may be right. I don't know about much glove because I never used glove. I only use Word2vec. Yeah.
Okay.
I thought it's glove is uses the skipgram model to identify vectors, and Word2vec I thought it was continuous backup words, but I may be wrong. Yeah. Okay. So if you can open the Word2vec file, and it's actually default code that's available in TensorFlow. I picked it up. I want to show you the fun thing in that. Some people may or may not know it. Okay. So it runs and then of course exits. If you're running it on your machine, go back to your folder wherever you're running it. There is a file called, okay, it's doing it right now. You see, I think it's learning. Let me see if I can. No, I can't increase the font size here, so you have to see. It's at the end of each epoch, each training round, it's picking some random words and then identifying what words occur closer to this word or which seem to be similar. Initially, for the first few rounds, it is very inaccurate, but as you go deeper into the training towards the later part, if it picks a word, let's say Washington, it picks up capital cities of other countries, which it found based on the text. I think it's Wikipedia text it's looking at. If you can run it on your machine, you can keep on looking at it, but I'll wait for it to run. I think it takes 5-10 seconds. I think I've already run it once, so I'll show you. There's a file that ends up creating called tsni.png. This is the image of file that gets created of all the words. Actually, you can see based on the corpora you're training this on, model will create vectors for each of the word, and when you post those vectors onto some sort of a vector space and you look at them, it's a n-dimensional image, but you're looking at it as a 2-dimensional image. When you look at that, words that occur frequently together would also appear in the image together, showing that the vector the vector you are creating, or the vector you are assigning to a word also is similar. In other words, I think they're capturing the essence of similar words have similar vectors and they co-occur, they appear closer. So let me see if I can give a specific example. I think with the text, like you have the European, Chinese, some countries there, German, but then I think it becomes English also. So you have it's French, it's picking up languages there. So when you run this on your computer and you can see this file, this is called word embeddings, which is a pictorial representation of how the vectors look when you put them onto a two-dimensional image, multidimensional in this case, to show that vectors are actually capturing the essence of which words are closer to each other. Okay, so let's get to this is a non-NLP solution, so I'm actually going to skip that and I'm going to go to magic of language translation. I'm actually going to tell you how to design a model that's going to do language translation. I'll talk about various building blocks on that. Yes, you had a question? Yeah, TSNE is an approach which actually reduces dimensionality just so that you can show it in a two-dimensional, but it's actually a multi-dimensional. It could be 200 or 300 dimensional. Oh, sorry. So sorry. Then ask me the question again. Sorry. One hot vector, yes, the dimensionality you cannot change because the dimensionality of each vector in a one hot vector method is the size of the vocab. In word2vec, yes, you can define the dimensionality. It can be 200, 300, 500. Typically, that's the number people use, 200 to 500 as a dimensionality of vectors. Okay, let's talk about machine translation if you're trying to use. So you will use sequence to sequence, and then more than sequence to sequence, you can use a decoder, encoder, decoder, and you can add attention on top of it. Now let me talk about how do you add a language model to it. So you actually have a sequence to sequence model. Let me define what a language model is. Language model, in a very, very simple term, is how to predict what the next word is given a few input words or the previous words. In other words, let's say you give an incomplete sentence to the model. It will predict what the next word would be. Or if you give a wrong sentence or a correct sentence, it actually gives you a probability of how right or how wrong the sentence is. So in other words, it's actually like a human being looking at the incomplete sentence, it will start predicting what the next word may be. The cat sat on the mat, if that's the sentence, the cat sat on, it'll be, the next word will be the, and after the it could be mat or a table or a chair. It predicts based on the training what the model has got. So language model is a single RNN on LSTM which reads, let's say Wikipedia. Many language models are trained on Wikipedia. It takes one word by one word and it makes a prediction at the end of the word, but it knows what the word is, so it takes the input as the correct answer and does the back propagation and then does the loss computation and back propagation. In other words, it's actually trying to assimilate what's in Wikipedia. Let's say if they have 3 million articles in Wikipedia, it actually reads the entire 3 million articles, and now it is intelligent enough to see how a sentence or a paragraph is written in Wikipedia. And because Wikipedia is generic enough for human communications, because it has articles on science and maths and technology and transport, travel and tourism, whatever, it has been exposed to so many types of sentences. It is a model well-versed in English language. So you can give an incomplete sentence, it predicts what the next word is. So that's a language model. So when you do a machine translation, and if you do an encoder and decoder, what is happening is, after you give the inputs, the model takes the hidden vector, the context vector, So you have the ST is the hidden state of translation model. TM is translation model. So you have a translation model which you have trained already, which is getting the creating its own hidden state, and in normal situation without a language model, what you would do is you use just this ST of TM to start making your predictions of YT, because that's what the YT you're trying to predict. But because the YT could be wrong, and to enhance the accuracy of prediction, before it predicts YT, it wants to use the hidden state of a language model too. So you're actually taking the help of a language model, and it says, hang on, as a translation model, I think the next word is the cat sat on his table, on my table, on it table. It makes, let's say it makes 3 predictions, seems to be high probability, it and him and is. A language model will look at those 3 top predictions, top K predictions, and then says, you know what, out of those 3 predictions, Mr. Language Model, translation model, I think the right word there should be on the or on his, whatever. It corrects the predictions given by the translation model. So let me explain again. So based on the translation model, you have a hidden state coming in. You also have a language model hidden state coming in. You combine the two mathematically. Of course, there's an attention mechanism here, and it uses the essence of a language model and a translation model to make the final prediction. And people have found this to have a higher accuracy. This is actually from a paper. It's published here. So they actually have 2 different models. You actually have a shallow integration and you have a deep integration. I won't go into the deep integration, but the essence in this paper is, for a regular translation model, instead of just using the encoder and decoder, if you combine a language model along with that to the encoder decoder, the accuracy of your translation goes up. There's another paper that came later. One of the biggest problems in translation is unknown words. Even though you have a 50,000 or 80,000 as your input tokens or input vocab, and another 50,000, 80,000 overlapping or not, vocab for the output vocab, the vocab for the output RNN, sometimes the model does not know what is the right word for this translation. 2 years ago, 3 years ago, models were trained, if you don't know what the word is, put an unk there. But obviously the quality of translation is not really high, so they have to figure out how to eliminate the unk. So one idea was, let's add a language model, which I just showed you in the previous slide. So adding a language model eliminates the possibility of unk, because if the translation model cannot figure out, the language model may be able to give you a few ideas. But even then, you still have unks. So the next idea was, during training, so you have a language translation training from English to French, and let's say you have 1 million sentences and connecting another 1 million sentences. While doing the training, the model actually creates a dictionary called alignment dictionary using attention model. Why? While translating this word, when I'm outputting this word, I knew using attention I had to focus on this word. So maybe the translation of this word is this word. So I'm actually having a one-to-one mapping, so I'm creating an alignment dictionary. So it creates an alignment dictionary during training, and when the training is done, when you're doing the inference, if you find an unk, even after using a language model, it goes and checks the alignment dictionary and say, okay, hang on, I don't know the translated word in the target language, but at least I know what was the word which I was translating it from. So I'm actually going to just put the source word right there. At least you have a sentence which is not dramatically wrong, and if you know hopefully the source language too, you'll be able to figure out. That was a step further to improve the accuracy of, so eliminating unks. So creating a word alignments was the other one. There's another technique people have used. That's a little more complicated. Let's say you have a corpora in source language and corpora in the target language, and you want to create a model that takes source and outputs in the target language. But if I have only 1 million sentences, how can I expand the sentences more so that I can have a smarter model? So they found first, okay, do I have a different set of target to source? I take a target corpora and convert that into a source language, attach a language model for that to bring it of higher accuracy. Now you have an additional corpora of your source language, and you can use that new source language and the original source language together as a bigger corpora, and you can train the model on that. So that was another model people have created called maximum mutual information in this paper. You can read that. So those are two techniques to improve the accuracy of translation. There's another technique. Let's say the model is translating the sentence, and the translated sentence till now is, I went to, and it has to predict the next word. Typically, prediction means the model is giving a probability number for each of the word in your vocab. That's what it means. And it's making a softmax predictions. But whatever is the right word, the probability is 0.99 or whatever, but the words which definitely not possible, it gives a probability of 0.001, 0.1, whatever. It gives low probability. So by picking the right threshold of your probabilities, you can pick the top word, and that's how prediction happens. But some people said, I went to, if the next word is the, it can be the, or it could be I went to, I don't know, let's say a different, I went to, what is that? I went to the conference. Now, instead of the, let's say I went to the movie, conference, play, and a game. Yeah, let's say those were the top 4 probabilities that came in. Of course, I went to the conference was the top probability, but the probability was 0.993, and the next probability was 0.992. Sometimes, just because something is the highest probability, you can't just take that. So they figured out, in a greedy search, the model doesn't care for what was the second probability word and how close was the probability to the top probability. Even if the top probability is a very, very minute change, it just takes that as the answer. That's called greedy search. It looks for the words in my vocab, decode vocab, with the highest probability, and I'll just take that. Whereas some people suggested, no, that's not going to work. I'm actually going to take the probability of the first word, like I, and then when I predict the second word, I compute a dot product of the probability I went, and when I make the third word, I went to, I'm actually doing a probability of the unigram, bigram, trigram, all the words before I'm done with the sentence. So mathematically, how expensive this computation is. Let's say the first word, when you're making a prediction, and if your vocab size is n, you have n predictions. Okay, you take all the n predictions, and when you make the second word prediction, you have n predictions there too. But in full search, what you're going to do is you pick every word in the first prediction and find out the n predictions that come next to it and do a probability of the bigram. So you take the first word and then go the first word, second word, third word, fourth word, all the way to n. Take the second word, then again first word, second word, third word, all the way to n. Third word. You're having a n times n computation. And if it goes to the third word, then you talk about n times 3. That's a computationally expensive search, It's called full search. People said that's not going to work, so they actually came out with a new technique called a beam search. You take the top K words, you don't like top 3, top 5 words, and you keep the top 5, and when you make the next prediction, you compare against those 5 words, not the entire n words. So so it will be 5n. So for each of the word you have n predictions, you have 5n. It's not n squared, but it's just a 5n, which is actually a lot cheaper. So beam search is a suggestion that is made when you're doing a language translation. So instead of picking the top probability, you go for the next, you take the top 5, top n, of k actually they call it. And there is another paper which came out where to increase the diversity, you actually can force some random rewards. You just give a random reward for the prediction, the probability prediction at each step. There are more tricks on how to get more data. I think I mentioned this. You actually you have a target to source, you do a conversion, and using a language model of the target language, you further process it to get extra corpora. I mentioned this already, but that's another way of increasing the accuracy because you have more data with you. This is the best paper if you really want to get into language translation. You want to read this. This is the Google paper which was published in 2016 December, I think, so hardly 8-10 months ago. This is the model they're using for the translation in the production stage. So if you're using a Google app for translation, this is the paper that's based on. They actually use lots of improvement techniques in this. For example, the encoder and decoder are multi-layer. It's 8-layer RNNs. And the encoder, at least in the first layer, is a bidirectional. What is a bidirectional RNN? Let's say there is a sentence called, I am going to the movies. And RNN, in unidirectional RNN, takes the first word I as a first time step, and the second word in second time step, and third word as a third time step. In a bidirectional, you have 2 RNNs. One is taking the sentence from left to right, and the other one is taking from right to left. So at any point of time, the hidden state of, let's say if you combine the hidden states of both the RNNs at every time step, that hidden state will not only have what was given as input in the past, it also knows what is going to come in the future, because the reverse directional RNN, which already has looked at the last words, and it has given that information to the hidden state. So you actually have the advantage of that. So you have a bidirectional RNN on the bottom layer. You also have a skip level connections where you are passing on the information of hidden states, which improve the accuracy and reduce the computational power, residual connections they call it. They did a beam search. Another problem of translation is you eliminated unks, but there's another problem called repetition of words. If the model does not know that I've already used this word for a same context, for a same meaning, it just may repeat the same word and same meaning again. Sometimes you find translation models or even summarization models repeating the words. To eliminate the repetition of words, there is something called coverage penalty. While outputting a word, if you go back and look at using attention, if you go and looking at word number 7 and 8, and if you think I've already looked at word 7 and 8, that means I've already got the essence out of the word, but I'm going back again, so I won't do the translation there. I do a coverage penalty. If I've already covered certain words in my input corpora, I won't do it again. That's called coverage penalty. So that eliminates repetition of words. Also for computation, low precision numbers, if you're using a 32-bit or a 16-bit computation, the mathematics you're using to compute your probabilities it's really high, computationally high. They found when you bring down the precision arithmetic to even 8-digit and 4-digit numbers, it lost hardly any accuracy. So, but that improved tremendously the computation time. Also, they identified some rare words. I think maybe in the other paper they have, when you put an unk, let's say you don't know what the meaning of the word is and you put an unk. But unk in the first sentence, unk in a third sentence, and unk in a seventh sentence looks like same because you put in the same unk, but they actually are referring to different words. So they found an alignment technique where even though they're putting an unk there, they're referring to the word which is triggering the unk, which gives a better understanding for a human being who's consuming the translation one. Also, they address the rare words in a different way. Let's say you have a sentence called a word called running, and the model could not find an appropriate translation of that. What it does is it actually goes and look at what was the word using attention and starts breaking the word into smaller pieces. It does maybe lemmatizes and stemmatizes, or it picks up a few characters. So if his running is the word it could not understand, it says, can I understand the word R? No, it doesn't make sense. Are you? No, it doesn't make sense. R-U-N? Yeah, it makes sense. So I'm actually going to pick piece of that word, translate, and highlight it. It's an incomplete translation, but at least instead of running, I found a word which is run, and I translated the word to this target language. So that's another way of identifying some rare words, where they start breaking the words into small pieces. This is an overall picture of the model. You can see on the left side multi-layer encoder. You actually have a skip level connections or residual connections. You actually have they're using LSTMs here, and attention is in the middle in the blue box, and then on the right side is the decoder, and there's a softmax blue top horizontal bar on the top, which is making a predictions on the probability prediction of the entire vocab, giving obviously the high probability for the right word and low probability the wrong word. That's a huge paper, I think, written by at least 10 guys in DeepMind and a bunch of other Google organizations, and this is what is in the production right now. One more, yes, sir. I don't know. I've not seen. There are at least 10 sensible, intelligent, groundbreaking papers published on a weekly basis. At least 10 I've seen. If any human being says that I've seen all the papers, I'll be surprised. And I even tell my company too, if I have to work for 3 days and meet customers and do product development and understand what it is, I need to study for 4 days, because I'll give an example. In image processing, around a year and a half ago came with a new model called RCNN. It's called Region Convolutional Neural Network, RCNN. It was smart, fast, it was doing an excellent job. 3 months later came something called Fast RCNN, which actually was computationally cheaper and more accurate. Another 6 months later, in other words, around 8 months ago, came called Faster RNN. And if I have not read the paper Faster RNN, if I'm meeting a customer or doing a product development, I'll be completely missing the boat, because Faster RNN is so fast. There's another model called YOLO, Y-O-L-O. You only look once is a model where they came out with YOLO 1 and YOLO 2 with 9 months of gap. YOLO 1 was able to process 45 FPS, frames per second. That is, if you hold a mobile device with YOLO running on it against some people or in the street, and it's constantly labeling the items it sees, let's say human beings, cars and chairs and bicycles, and if you move, it can be very accurately predicting if you have not more than 45 frames per second, which was supposed to be really fast. 8 months ago came with a new model which does 220 frames per second. A lightweight image processing model which runs on your mobile device. So going back to your question, I don't know the answer for the Microsoft paper, but I'm sure there must be a paper. And this is the last slide on translation. I may have given an impression to you that when you're doing a translation from one language to the other language, let's say source language and a target language, that is English and French, you will have only English and French. But there are papers published where you can have a single model which will help you translate into multiple languages at the same time. So you have an input language called English, but if you have a French, German, and I think Japanese and French, Chinese I think is less, but French and Spanish and Dutch, you can actually train a single model which will understand how to understand one language to multiple languages, and during inference, it actually helps you translate into all the 4 languages in one go. That's another technique too, but the mathematics of it is very similar. You look at the encoder, it is a bidirectional encoder. I think it's a multi-layer encoder here, and the hidden states at the end of each is being supplied to different decoders, and each decoder is learning for that specific language. And when you're training, you give a correct answer. What's the correct answer in French and Spanish and Dutch and Portuguese, and then model becomes intelligent. But the funny thing is, there's a same encoder that is feeding into it. So it's the same set of hidden states going in, and the hidden state gets smarter and smarter to figure out what should be the weights for different types of languages. It's amazing. So let's talk about summarization. I'm looking at time, and I know I'm trying to get information to you as much as possible. I have summarization and question and answers, but I think we have 1 more hour. I'll try to do summarization, because summarization is another extremely important topic, like topic modeling, or if you have a huge amount of text, how do I get extract the right information? Also, you can use the same approach for doing question answers too, but I'll talk about that. You had a question, sir? Three years ago, there used to be models where there used to be one common language. Let's say if I have a French and German, I want to do a translation, you used to do French to English first, English to German. That used to be the case, but now there are models available which will do for whatever language you want. But again, the availability of corpora is an issue. So for example, Arabic, Chinese, Japanese, there's not much of research done, even though there are papers published. If you go to Stanford website, there are some reports on Arabic and things, but there's not enough corpora available. French and German and English, also they're structurally similar language, I'm told. I don't know German and French, but based on what I'm reading, it goes from left to right. It has a subject, verb, and object, and the structure of a sentence is very similar, if not exactly the same, for these languages, and hence it's easier to find corpora and easier to do the translations. But if you have a Chinese as a language, a Japanese as a language, where the first word and the second word in the source language may appear towards the end and vice versa, whatever, and then creating such a model will be difficult, because if the sentence is 20 words long, and then you have an attention problem and assimilation problem, vanishing gradients, all of those things. Which paper you're talking about? I think question is 2 slides ago you showed a model. Does it have a language model? Which one? This one? This one, I don't think they have a language model encapsulated in this. At least I have not seen in. No, I don't think so. Google does not have the language model attached to this. No. Trained language model, yeah. You already have lots of trained language models available. If it's in English, no problem. There are free open source language models available. If it's a French or some other language, I think you got to struggle for it. But you can be a pre-trained language models used. You don't have to train simultaneously. Pre-train. Yes, sir. 5 minutes break. Okay, let's take a 5 minutes break, please. Yeah. Okay. If you're looking for tools, I may not be able to answer this question right away. Maybe we can. Oh yeah. I'll talk about the algorithm summarization. I think we can take that. Yeah. Sure. For those guys who are back and sitting in the room and trying to relax, if you want me to say something, one question that's boggling many project managers and managers as such, this is a question for managers, that means. You guys need to do research on, and we all need to do research on how pyramids were constructed. If you are a project manager, do you know how to plan to construct a pyramid? Think about that. Sorry? Yeah, the pyramid, yeah. The Egyptian pyramids, yes. Yeah. No LDA. No, I don't respect LDA anymore. I don't care, no. It's an old technology, yeah. It's at least 3-4 years old. If you take a couple of GPUs, let's say 4 or 5 GPUs, it takes 2 to 3 weeks, depending upon how complex the model is, for a translation or summarization. People are trying to cut down the amount of data set so that they can do it in a day or two, because 4 to 3 weeks, even if you have 4, 5, or 10 GPUs, it's just not possible, because you can't train, you can't go back and modify and check all of that stuff. Yeah. So that's an approximate size. 1 million data points, inputs with 5 to 10 GPUs, takes 2 to 3 weeks.
So when you say data points like million
Sentences, yeah.
in English and then
And French, yeah, for example. Oh yeah. And it will be even more depending upon what's the stack, how many layers you have stacked. All of that stuff too, even what will be the drop-off rate, and so many different factors there, yeah.
and still how accurate that in the production system are they
Yeah.
using the deep learning, this RNN LSTM model?
Right now, all production systems for translation by any of the big companies are all deep models only.
How accurate they are? Like what do they separate?
The published reports, they use something score called Blue Score and Rogue Scores. Then 50 or 60% is the highest number I've seen being accurate in translation and summarization. Summarization is even more difficult. I'll talk about that, because you can have, if it's a translation, there is a right way of translating and a wrong way of translating. That's period. You know that very well. But summarization, you could do a different way and I could do it differently, and both are right. So that's where I think the Blue Scores are being used and Rogue Score. But in translation, I think 50-60% is what the accuracy rates are. So if you use a Google translator, I think I've seen when I go to Brazil, my Brazilian friends with Portuguese, and they'll be smiling and laughing, because I think when I say something in English, I don't know whether it's doing correct or not, but obviously it's doing something else. Yeah.
What about language correction? Language detection. For example, you have the first unknown case, and then you feed it to it, and you know what language this sentence is before feeding the language speaker. Is that even a way?
You can, if the model is, can I just predict what language it is, or that's even a simpler problem. That's a simpler problem. You can just feed a bunch of sentences and say this. You just give a class name called language, and then with a few, maybe 10,000, 100,000 sentences, it will figure out what language it is. That's easier. Yeah.
After you figure the language, then you feed it to the per language specific model to get
No. You don't even need to. Let's say you have trained a model which will do English to French, let's say, but you're giving in German. It'll tell you, oh, this is not even English, so it will not do anything there. Yeah, it'll figure out if this is not English.
one unified model that you can input any kind of language and then translate it to, like what would happen.
That model I have not seen. Multiple to multiple I have not seen. One to multiple I have seen. I just showed you the slide. So from English to so many different languages you can do. So you give one English language sentence, it does simultaneously to all other languages. But any language you give to any language, I don't think there is a model. I don't know. I'm not sure. Yeah. I've not heard of transfer learnings in NLP. I've seen more of the image processing. Yeah. Yes, in a couple of days, I'm actually going to have the video and the slides together available. Yeah, I think maybe an email will be sent to all the attendees, but I'll be posting on my LinkedIn too. So my LinkedIn is, I'll actually I have a YouTube channel, so I'll put it in the Gym channel and then link it from my LinkedIn.
Can you comment on using CNN versus LSTM? Because usually we find LSTM is very slow for training.
Yeah.
CNN model.
Yeah, there are a couple of advantages of CNNs. For example, you can do you can parallelize a lot of training if you're doing CNNs, number one. RNNs and LSTMs are sequential, but even though there are only a couple of papers which have used CNNs to do processing text, 90%, 95% of the papers are using only LSTMs or RNN variations for text processing. People don't use CNNs. There are some papers used, but I would do, if I would do, I will do an RNN or LSTM or a GRU, but not CNN. Yeah.
Can you comment on like Chinese language? Because I see you mentioned a paper using one single model for multiple languages, but not including like Chinese languages.
Forget about the multiple languages. There are fewer models available from English to Chinese because of the way the language, Chinese language is structured compared to an English sentence. You need to have a lot more data set, and they're not able to create so much of data set at this point of time. There are a couple of papers published, but I think the accuracy rates are so low because they don't have enough data set for that. But they have tried to prove the concept, yes, you can work for any language, so you can take an English to, let's say, even Arabic or even French, Arabic and Chinese and Japanese, because they're all differently structured languages compared to English. Yeah, yeah. There are papers available, yeah. When you're training a model, you have to be a big company or a big organization. Individuals cannot do it, because you and me, if you have just a regular laptop or a desktop, it takes just one compilation or one training will take, let's say, 2 to 3 weeks or 4 weeks. And if you want to make a minor correction, it'll take another 4 weeks, and you'll get bored really. If you're an organization, what they do is it takes still 2 to 3 weeks for a training, and that's why they're trying to see if we can reduce the number of parameters and reduce the computation time, even sacrificing the quality. That's why you don't see models increasing the accuracy rates faster, because it takes, unless you come out with the newer techniques, with the existing techniques, it takes more and more time, and people just don't have time. Like for example, if you are a researcher, PhD guy, you got to publish at least 20 papers in 5 years so that you can get out of your PhD, and you don't have time months after months to do that. Same is the case with organizations. So they have quarterly results, they can't wait for 2 years to actually do one research. No, those are two different things. You actually have one model trained and you put it in the production. You can continue training with the other model. Oh, people are doing it all the time. So they train it for, let's say, 6 weeks, take it out and put it in production, and then continue with the training again. We have more data coming in and start training it. After 6 weeks, they'd stop it, take the state, whatever it is. Well, they are updating. I'm just predicting, I'm just randomly saying number 6 weeks. It could be every week too, but you don't have, if you have to add some data and retrain a model, unless you're doing a reinforcement learning, which I don't know how they do it, I'm sure that you can, transfer learning, sorry, maybe you can just take maybe another extra 1 week, but if you're doing retraining the entire model, starting from scratch, it's going to take 6 weeks plus another week. They won't give. That's the money. They're actually paying money to actually get that. So what they're doing is they're actually hiring companies like Crowdflower is one data creation company. Crowdflower, Mechanical Turk, another company called Amazon company. They're actually creating data sets. So you pay a lot of money. You go to cheaper countries, or rather countries where the resources are available freely and more cheaper, let's say Philippines, Vietnam, India, China, and there are people sitting there in offices and they're trying to translate or annotating. They're actually, let's say if it's a contract management software, someone is sitting and say, looking at the sentence, this one is a termination clause, this is non-compete clause, this is whatever clause, they're identifying clauses, people sitting together, down and human beings, and creating data sets. Then you can, so if whoever is doing it, that's their money. That's why if you want to start a company, that's where the money is too, creating data set. Yeah, yeah. There's lots of rules you need to write. You have a bunch of big rule engine you have to write. Number one, for example, if you see a problem, a lot of people using shortcuts. That's not an NLP problem. It's a pure software problem. Figure out what the shortcuts are, have a dictionary, and then update, modify it. Number two, if people are using abbreviations and stuff, that's another dictionary problem. So you just write a rule engine there. But once you eliminate the unknowns, the abbreviations, shortcuts, and all the things, now we have a full text. Now, then use the NLP on top to extract the meaning on that. Extracting meaning is a big problem. A lot of people at the companies trying to figure out intent, extracting intent from a sentence. Like for example, if a contract says, in a clause says, the supplier will pay a penalty of 5% if the quality of the production in this 1 year is worse than 10%, let's say. You have so much of information that one sentence, unless a human being sits down, you can't understand. But they're trying to define models, how to understand that complete sentence and identify actionable. I talked about sentence chunking and segmentations of sentences. It actually picks sensible sentences. If the supplier will pay a penalty. You just pick up that and say, okay, there is a potential possibility of supplier paying the penalty. So look at the other chunk. As I say, it says if the quality is less than 10%, pay a penalty of $10, whatever. So you pick up that and say, okay, let's see, can I write a rule engine which will connect with this and this, but there's a lot of software there. There's so many companies working on that, no one has figured out. Yeah. It depends. If it's an academic world, yes, people have to publish how good the model is because otherwise no one knows what it is. But if it's a company, if you're screwed if it's inaccurate. If it's a legal or a regulated industry, you are stuck. If it's a non-regulated industry, people want to bring it up as high quality as possible. People like you and me will be posting on Facebook and LinkedIn sort of how bad the model is, and that itself is a good indicator of how bad accuracy. There are no tools available. So for example, translation, there's a rogue score or a blue score for translation. Well, the translation is, if you want to, let's say I give you a paragraph and your model does a translation. And then you ask a third person to do a translation too. So you have model created translation and a human created translation. How do you find out which one is better? People are saying, okay, if there are single words, bigrams and trigrams, matching words available, the more number of words in a machine translated are available compared to a human translated, that means the machine translated is closer to the human translated and hence it's better. So for mathematical purposes, they're comparing how many trigrams in a machine translated model matches with the human translated. If you have 30 out of 300 are matching, that's my accuracy. But if I have only 300 bigrams in my intro translated, all of them match with the human translated, that is 100 or 300 bigrams with 300 bigrams in that. So it's 100% accuracy. That's another problem too. Yeah, that's another problem too. So they're trying to do, at least they'll use 2 different human beings and say compare between the 2. But they need to have human being a standard person. Actually, yeah, in GRE and GMAT exams, I'm told when you write the essay as a test, the model actually is doing an analysis how good the model is, how good the essay is, and giving a score. So what they do is they randomly pick once in a while and give it to a human being. And then without telling what the score was, and they're comparing constantly to see whether the model is still intelligent or not. Apparently it was good, it's still going on fine. So there is model is improving, but anyway, we need to get back, and then 12:30 I want to stop, yeah. Okay, gentlemen, ladies, let's start summarization. I will not talk about the question answering. When you create a neural network to do a translation, summarization, you give a larger text and it outputs a shorter text. If you take that approach to the extreme, it can also be used for topic modeling. Let's say you have an article, you are a news reporter or a news reporting organization, and you just got a write-up from a person who talks about the scandals going on in football and money laundering and Las Vegas casinos. Do you want to connect that with a casino or a scandal or Las Vegas or a sport? It could be any type, it can fit into any topic. So topic modeling, to identify what topic this fits into, would be another variation of summarization. But if you just want to create a summary of a larger text, you can use neural networks too. The biggest difference of summarization compared to translation is, there is a right translation, there's a wrong translation, period. So you know what was the right thing and the wrong thing. If the model makes a mistake, you say that's a mistake. But in translation, unless the model makes a tremendously wrong translation, wrong words, words, gibberish words, then you can say it's a bad summarization. But summarization per se itself is so human specific. The way I would summarize a large text would be different from the way you would do and other people do. So comparing how good a model was when you do a summarization is always a difficult task, and how to compare how good the model is. And even getting, for training purposes too, for you to create a corpora or a training data set of variety of summarizations, it's not easy. So we'll talk about that. So again, you will use a sequence-to-sequence model here too, and you will even use a bidirectional sequence-to-sequence. Again, the advantage of a bidirectional compared to a unidirectional is the unidirectional only knows what was the inputs in the past, whereas in bidirectional, it also knows what was the inputs in the future. So this is the paper published by the gentleman I mentioned to you earlier, Richard Socher, and a few other guys. I think they did it in 2016, I guess. So it's not too long ago. Which year are we in? 2017. So it's less than a year ago. This paper was published, and in addition to using just the regular sequence-to-sequence or bidirectional sequence-to-sequence model, they've actually implemented a few techniques which actually improved the summarization outcomes a lot. So as of today, I think, so he's part of Salesforce, so I guess the Salesforce summarization model is the best model as far as I know, unless something has happened in the last 10 hours, I would not know. So in a very simple language, if you look into summarization, you have an encoder and a decoder, you have a series of inputs coming into encoder, it's a bidirectional LSTM or a GRU, and the last hidden state is given to a decoder LSTM, and this is not obviously it doesn't make sense to have a bidirectional here because there's no, you don't know what the future is because you're doing and then you start outputting and then figure out, train the model in the process, like a typical sequence-to-sequence or encoder-decoder model. But here what they have done is, in addition to having they implemented attention, but they implemented an entirely new technique, which is what I want to really highlight. There is something called reinforcement learning. What's reinforcement learning? This approach is used for in robotics and games and defining and training neural networks to play games. So let me give an example in the context of game. Let's say you play a chess game, a game of chess. Yeah, two players play. Let's say the game is actually being played between two international grandmasters. Yeah, you're aware of the term grandmasters? And grandmasters are extremely talented people. They know how to play chess. But when two grandmasters play, one person wins, one person loses, right? Is the losing grandmaster any bad player? He or she is an extremely intelligent and smart player. But based on a series of steps, even though at any point the step was the right step to take, among all the steps you can take, you pick a step and then you move that. But over a period of, let's say, 10, 20, 15 moves, you figure out one series of moves was the right thing to do and one series of moves was the wrong thing to do, right? So how would you train a model in such an instance where you don't know what is right or wrong at every step, but you know at the end of the series of steps? It's called reinforcement learning. So you have the concept is you have a state, what state the game is in, you have an action, the agent takes an action, and you have a rewarding policy. The model, you will tell the model whether this was the right thing, this is the wrong thing, but you are telling this after a series of actions you have taken. Long story short, reinforcement learning is, if you don't know the right or wrong answer after every step, but you can only know at the end of 10 steps, you train the model by telling at the end of the 10 steps. So they've used the same approach here. So in addition to the regular training of a summarization technique where you have a large text and some human being has created a shorter text, which is summarized text. They train the model first, they input the large text, and when the model is outputting, the decoder is outputting the summarized text, you compare word by word to tell the model whether it's right or wrong. That's the traditional approach, which we've already seen. On top of this, they said, okay, we are going to use reinforcement learning, where we will put the entire summarized, human summarized version as an input. So you give the large text, let model summarize the entire text. At the end of the entire summarization, you tell whether that was the right thing or the wrong thing compared to the human created summary. So it's like, instead of waiting for word by word accuracy prediction or correction, you're actually going for the entire summarization done. So that's the picture there, or the circular picture there, the reinforcement learning. How they did it, I think you got to read the paper, but the overall concept is, in addition to the encoder decoder, in addition to attention model, and in addition to using bidirectional encoder technique here, they also used reinforcement learning to enhance the accuracy of summarization. So let me show the picture in a different way. Also, when they did the regular training, you have the attention. The attention is till now, if you paid attention, attention is always on the encoder side, because the decoder will go look into the encoder for 7th word and the 10th word. So you're actually paying attention on the encoder side. But here they actually introduced an attention to the decoder too. And this was primarily to avoid repetition of words. In other words, when it goes back and checks itself what it has produced as a summary, it will also figure out, hang on, I've already converted that, I've already summarized that message, or I've already used that message in summarization, so I should not go there. So if you look into the context vector, you have the context vector of the encoder, you have the context vector of the decoder, and you have the current context vector of the decoder. I'll show it on this side too. So you have the context vector of the encoder, and you have the context vector of the decoder, and let me see what the alphabet is. H is the current context vector of the decoder at that timestamp t. And based on all these three hidden vectors, or hidden vectors, the model makes a prediction on what the right word is on the entire vocab. If you have 50,000 words, it actually makes a prediction. So instead of just using only one, it does all the three context vectors. So that's one idea when you're making a summarization model. So you use the same techniques, which I taught you earlier in the morning, like you have the sequence to sequence, encoder, attention, and you can use bidirectional, you can use attention for the decoder, all of those ideas. This is another improvement on top of the previous one. People, if you look into human beings, when you do a summarization, you actually don't read only once, you actually read twice to summarize, at least for me. I need to read everything 2 times. So if you look into the model, it reads the entire text once, and when it's reading the entire text the second time, it actually takes the hidden state of the first encoder. So you have encoder 1 and encoder 2. Encoder 1 talks about first reading, and encoder 2 is the second reading, and of course you have the decoder. That's the overall structure, but let me explain how the model works. Okay. So after the encoder 1 is done, all that you're taking from encoder 1 is just the hidden state. So in the detailed explanation here, let's not show the encoder 1. So you have the encoder 2, hidden state that's coming out. Encoder 2, this is hidden state at first time step of encoder 2. The number 2 or the superscript is referring to the number of the encoder. So you have encoder 2 taking in the information. At every time step, it is using that information to compute a overall context vector which will be used by the decoder to make a prediction. But while doing it, it also wants to go back and look at a factor of the hidden state. It's called pointer. This is called pointer networks, P1, P2, P3. These are various pointers trying to point to the words in the input text. So there's the encoder text, which will decide, the model will decide based on the training, if I know the word to summarize, I will pick up the word from my decoder vocab, I will pick it up and put it there. If I don't find the right word in my decoder vocab, I'm actually going to look into the encoder vocab, which is, I know the entire context because the large text. I'm going to pick the word from there, and when to pick, when not to pick is the training of these pointers. So pointers will give a factor of when to pick and when not to pick, and when to pick, you actually identifies which word to pick from. To summarize in this case, the improvement from the previous paper is you read not once, but you read twice. Now you can say, can you read third time? I'm sure you can, but there's no paper published on that. So you can read the second time. After you read the second time, you pass on the hidden state and start making predictions. But in the process of making predictions, you also need to figure out, if you don't have the right word in your decoder vocab, you should also have the option of picking the word from the encoder vocab. So when to copy from the encoder versus when to pick from the decoder is a pointer mechanism. So this concept is called pointer mechanism, which is being implemented. This is part of the training, similar to the attention training, where you will let the hidden states, when you're training, you can find the scalar number which multiplies each of the hidden state and tells the model, and model over a period of time figures out which word to focus, or the attention mechanism in which area to focus on the inputs. Similar is that even the pointer mechanism too, the model figures out where to pick the word from and at what time to pick the word from the encoder vocab compared to the decoder vocab. That's the read again and copy model, which was published, I think, again in 2016, if I remember correctly, yeah, or maybe 2017. Okay, here is the complicated picture. Take a second to read it. At least look at just the top left picture. Look at the number of arrows. So here is the encoder 1. So you give a time step t, you give the first input, and you initialize the encoder to the hidden state being zeros at the starting point. And at the end of the first input, there is a hidden state called H11. Yeah, H11. The subscript 1 is to refer to the time step 1, and superscript 1 refers to the encoder 1. And so you do the entire training first for the encoder. Even though in the picture it looks like you're doing simultaneously, you got to do all of these, the entire encoder 1 training, and you store the hidden states for every time step. So when you start training this encoder 2, you again initialize the hidden state of encoder 2 with zeros. You give the input x1, you give the hidden state at time step 1 from encoder 1 as another input. You also give the last hidden state at the end of the sentence of hidden state of encoder 1 as an input here. So this last dotted arrow that's going in is the sentence hidden state. That is, at the end of a sentence, you have a new hidden state that goes into. So there's so much of information. You are getting not just the current word, you are getting the hidden state of the current word for the previous encoder. You are getting the last hidden state, in other words, the end of sentence hidden state for the first sentence from encoder 1. All of these inputs are going in. But here is the best complicated part. I think it is in the next picture, I think. Let me complicate it a little more. No, it's right here itself. So look at the next picture now on the right bottom. So it's the same picture but a little more expanded because you have a global hidden state too. So look at here. At time step 1, it has the initial hidden state initialized to 0. You have H1 coming in. You have the hidden state at time step from encoder 1. You have the sentence end encoder coming in from encoder 1. You are also getting a global, you see H global here. That is the hidden state of the entire, of encoder 1, of the entire text. So you have from encoder 1, you have the word hidden state, sentence hidden state, and the entire text hidden state. All of those coming in to process. So these are the two spectacular papers I have seen in summarization, but if you see, the fundamental concepts are almost the same. You have the encoder decoder, you have attention on the encoder, attention on the decoder, you have bidirectionality, you're using pointers, you're trying to, in this place, you're using reread, and in places where you have unks, whether summarization or translation, you try to go back and pick some words from your input source, and you can also split the input words. If you don't find the right word, split the words and take a smaller piece of the input word to see if you can do a translation or as is copy onto the output. So these are the 6 or 7 techniques almost used in almost every other situation. So if you go back and read papers, or if you run some of the models available, I think you'll be able to enjoy that. But I want to actually run, I know I have question answering, but I want to run this hands-on thing called generating text. I mentioned this to you earlier in the Shakespeare example where you can train a model which will generate a text. So I've created 2 LSTM models. I've shared both the files. One is called generate text, and there's another one called generate text large LSTM, I think is the name of the file. And both the files I've already trained long back. Each one takes, I think one took how many, 30 hours something, and the second one took around 60 hours. Yeah, to train. So I've already trained the model and I've given you the weights. So if you, all the information is in the directory. I'll show you the files. I can't increase the size of this. You see the weights improvement 15. This is the I think 15th epoch I think I picked. 1.5805 is the error rate, and this is for the bigger LSTM, and the one below is the smaller LSTM. You can see on your file too the weights improvement 19 -1.945. 1.945 is the error rate after the 19th epoch. That's for a smaller one. So if I run the model now, I'll show you it generates text right in front of you. Let me again I open it. I say okay. I open the file called generate text. So this is so I'm training a model based on the story Alice in the Wonderland. I'm actually training the model. So the model understands how English sentences are created in the book called Alice in the Wonderland. So the whole world, it thinks the whole world is just Alice in the Wonderland. It looks at the text and trains a model. The model is already trained, but when I run it again, what it does is it actually looks for the instance of the model right there and then picks that up, and in a few seconds it creates a new text. And I want you to see how good or not so good the so it has total characters of 16,000, total vocab 58, with a seed input. So she was considering in her own mind as well as she could, for the hot day made her feel very. That was the seed input sentence, and based on that, it's going to create some text. And this is, every time it creates different text, but why is it taking so much time? It should not take so much time. Okay. So let me copy this. So this is the text it created. Let me copy this and show it to you on a bigger screen. Of course, it's gibberish, but it is trying to understand. See, there's a word called U, Y-O-U, D-H-E, A and D. It figured out, I think, a few words, but it is still learning. But this is a smaller model which I did not give enough LSTM capability to actually process the whole stuff. And also I did not let it train for longer epochs. The one is only, I think, 10 or 15 epochs, and the other one is a longer epoch. So this is the text it's creating randomly, completely randomly. If I run the model again, it will create some other text, but that's based on just that one text called, story called Alice in Wonderland. Now what I'm going to do is I'm actually going to run the other file, which is actually a bigger file. No, this. The seed I'm giving Reddy, she thought rightly too, the very few little girls of her age knew the meaning of it all. So I'm just picking randomly 100 characters and then giving it as a seed, so that it will think that's the input and it starts creating based on that text. Yeah, I was running it on my desktop, so it was taking less time, but because the laptop I think is taking a little longer. In desktop, I have a 32 GB RAM, so it takes maybe 2-3 seconds, and this one is taking around 10-15 seconds. When you're using any NLP solutions and you try to define any models for yourself, I think take smaller data sets and small models so that you can actually see the compilation happening, and then, so let me look at this tag. It's not picking up. This is a bigger model. Look at two interesting aspects in this. There are not too many errors in the spellings. See, you can see let me get my. There's a was, the, door, with, the, doors, I don't know what it is, of, the, te, I don't know, of. The model has become a lot more intelligent. It figured out what's the right way of spelling the words. Of course, there's some random words like duros or whatever. Number one, and even shat and something. But that's one. Second is it's repeating. You can see the door with the doris, door with the doris, door with the doris. So it's repeating. This is one of the biggest problems in any translation or summarization. But in this case, because the model is not industry production level model, that's why I think it's not really up to the mark. But you can run this model when you go home to see how it works. Actually, if you don't use the weights I've given, it'll run at least for, I think, 60 hours. So it'll be running on your desktop. Leave it for a few days and come back. And when it's done, you can, it actually stores the model at every time step. I think it actually creates a copy of it. You all have multiple copies of the model. You can take the model with the lowest inaccuracy rate, and then you can use that for inference. And this is the inference. This is actually, when I saw it's scary, because the model is just on one book with the training of 6 days on a desktop. It's actually creating text which is similar to a human being text. If I do a little more bigger size corpora and do a little more longer training, maybe I can write a nice story of it. Yes, sir. Uh-huh. Yeah, my plan was not to explain the code, but I can explain to you on offline. In 4 hours, this is what my plan was to share. Yeah, no, I cannot. Yeah.
Yeah, one quick question.
Yeah.
You said that you give a zip sentence, so you give paragraph in that negative.
The way it's trained is, it is trained on 100 characters. So it actually takes series of 100 characters and creates the next set of 100 characters, and based on that it creates another set of 100 characters. So to start that model to start developing some new text, I gave 100 characters. I said, okay, based on these 100 characters, can you start developing? I don't think it makes any difference if I even give, let's say, 100 words or 200 words. I don't think it makes. It only takes the last 100 characters. That's how it has been trained. If I say, okay, based on a seed of, I could even train on based on just the seed of one character, start creating the next characters. The important aspect is, even if it's 100 characters, the model is trained on characters. So it actually picks what character comes after what and what makes sense and when to put a blank. So even though the model ran for 6 days on my computer, but with one corpora of Alice in Wonderland and training that and creating human-like language was the amazing part of it. Then of course you guys need to experiment more. And also the code thing, sorry. Lot of code is available online. I'm sure you can write code from scratch. I would never do that. I would just pick up the code existing from GitHub and other places and start modifying it and doing it that way. And yeah, that I think is making more sense. That's the reason why I think I have this code right there. And maybe that's another reason why I'm not able to explain the whole stuff, because I've not written the code myself. I just picked up the code and then and start modifying it and showing as an example. Yeah.
Is this some publicly available package, Python package that is being used for?
This is, I think I mentioned, this example is publicly available as a blog written by some gentleman. Let me see, I might have referred it in my, actually it's yeah, it's in this blog which is mentioned at the bottom. Yeah, I picked up the code from there, yeah. Using a language model. Language model actually figures out if some word is a correct word or not, and the correct word includes your spelling mistakes and sometimes even the position of the word too. If in a sentence, if the word is the wrong position, if it is wrongly spelled, it picks up immediately. So that the solution will be a language model, just using a language model. How can it do it? No, in this model what I've done is it's actually creating characters. So it's actually trying to learn what characters come after what characters, and that is based on the Alice in Wonderland story. So it has read the entire story, maybe 100,000 or maybe 1 million of the characters. It figured out after some time, okay, when a W comes and A comes after that and S comes after that, many times when the W and A, S and S come after that, there should be a blank, because that's how the next character is blank. So it figures out over a period of time. But it could still not figure out the doers. There was no word, but it thought that was a sequence of 7 characters comes one next to each other. After that, a blank comes. So it does not even know what it's writing. It doesn't make a understanding sense of the text, but it's just creating the text. The point I'm trying to make when I show this is, you can create a model which actually can understand, given a large amount of text, it understands how the text is written. So using that technique, you can, if you're doing a translation or a spelling correction, topic modeling, question answering, summarization, you can do a little more tweaking, and model will figure out, okay, for such a large text, I need to put output only, let's say, 100 words, because that's what I've been trained, and that is nothing else but summarization. But it does not know it's doing summarization. It just thinks, okay, for that particular model, if you give this much text, it gives this much of text. That's the only thing it can do. And it does not know the logic why it's doing it. Yes. For summarization, I don't know, but I don't think so too. Yeah. You can run AWS too. Yeah, it can. Yes, and a GPU I think may take quite short time, maybe 4 or 5 hours. This took like 60 hours for me on a iMac i7.
Spending $10, I should bring it down to 10 minutes. Sorry, no. It was a joke, okay.
Yeah, 10 minutes, I don't know, but yeah, I think it's considerably 10 times, at least 20 times lesser time compared to a CPU, yeah. That's all I had to share for today, but if you have any questions, I'll take, and we have 8 more minutes, but a long time ago, I asked a professor, yes, sir. Kinda I addressed. Of late, people use LSTMs and GRUs, that's it. Not too much of RNNs, and you're doing a text processing. Majority of the times, there are some instances where people are using RNNs. The primary problem of RNN, because of which in text processing people prefer LSTM and GRUs, is vanishing gradients or exploding gradients. In other words, a longer sequence, longer than 10 words, an RNN cannot manage. But if you look into carefully, an RNN and LSTM and GRU, all are RNNs, or are some variations of recurrent neural networks. LSTM works differently, but it's again another RNN too. In other words, it actually, because it has multiple gates called input, output, forget gates, it knows what information to save and throw away and other stuff. So it is efficient in some way. I have not seen a paper, but I'll not be surprised if I see a paper where, you know what, this LSTM which is trying to forget and ignore some data, which actually is creating some inefficiency. I would rather go for a higher capability RNN because it never ignores anything and it's more efficient and intelligent. That may be a possibility, but right now I have not seen a paper like that. So with the industry knowledge today, if you're trying to use text processing and using a deep networks, use LSTMs. And between LSTMs and GRUs, I've seen lots of papers published where they seem to be almost similar, but LSTM seems to be in some cases better than GRUs too. So of the 3 variations, if I want to recommend, use LSTMs. So word to vector is a technique of creating a vector out of a word. But topic modeling is a training you give to the model. So if you have a corpora of lots of text with topics already modeled, you train the model with that input text and the topic models, and it understands, okay, if this much of text, these are the words you are putting as a topic modeling, then it looks for some understanding from the text and adjusts its weights, and eventually that particular model will only do topic modeling, but it becomes intelligent in topic modeling if you give a large text because you have trained it in that way.
Yeah, one more last one. So does one vector also looks at complete word or character by character?
Word. Yes, sir. No, you're not inputting stop words. No, you're giving the entire text. Yeah. Yes. See, stop word removal, stemming, etc. is used if you have a text where you're processing, trying to extract information, extract meaning, intent. Sometimes you're trying to do that, but if that's not even deep learning. That's not deep learning. That's a regular NLP. But in deep learning, especially for problem areas like summarization, question answering, translation, you use deep learning models where you have to have a input and output data, lots of data sets, and you train the model. That's entirely different thing. You don't take out the text at the time, because the model has to look at some of the stop words too. You can't lematize and stematize. But when you're doing translation in some situations where it could not find the right word, in place of putting "unk," what it does is it picks a word and breaks the word, and in that process, you need to lemmatize. Maybe you just need to tokenize. You need to just pick only in character by character. At that time, you may use some of this technique, but that's a pure software programming activity, where you just invoke an NLTK statement, get the information, pass it on to the model looks at it, and then uses it. Yes, sir.
Do you have a way to, normally it's take a long time to train the model, right? Do you have a way to see the progress beside the tensor board?
Yes. You have a tensor board, that's one way of looking at it. Second is when you're training the model, after each epoch, you can actually write a program in such a way, it takes a dump and makes a statement to you, okay, I've done with the first epoch, second epoch. It can keep the information informed to you. So, and also after the end of each epoch, you normally store the weights, you store the model, because many times if something goes wrong with the machine or a power cut or some problem, you don't want the whole thing to be repeated again. So what people do is, at the end of each epoch, you just store the model state at that time and then keep on doing training. Because something goes wrong, then at least you can start from there. That's the only way you'll figure out what the progress is. Yes. Go ahead. Visualization per se, it's actually a great thing to understand the inner workings of a model. Let's say if you look at a tensor board, it actually tells you how the model is evolving, what the accuracy rates are changing and moving, what may be the reasons, what data is just coming in. It's a good learning tool if you're doing research or even production in companies too. I have not used visualization tools as much. I was academically curious, so I did a few times. But for me, if I've done a good design of the model, I run it and then do something else, because the model is training. It's going to take a few days or a few hours and stuff. I don't really care for the visualizations per se. So I'm not that keen on visualization per se. I don't see any of the benefit except the fact that you can see how it's evolving. But that's an interesting aspect of how it's evolving.
One question for you. I'm confused about epoch and iteration, I mean, in my mind, I somehow understand epoch is a like unit of time. I'm thinking.
Yeah.
So I'm confused about epoch and iteration. If you could explain that.
Yeah. Epoch is one set of training of the entire data set. And you could do that in mini batches. Let's say if you have 1 million records, if you process the entire 1 million records, you can say you are done with one epoch. But you won't send all the 1 million records in one go. You send in batches of, let's say, 50, 100, whatever numbers. So you have that's called mini batches. You actually send it. So you have 100 mini batches, and after 100 mini batches, you're done with the entire data. That's called an epoch. So each mini batch is an iteration. You're doing an iteration of training. It's sending information, it's doing a back propagation, understanding, becoming wiser, waiting for the next input. And if you do an epoch, you've done all the data, it becomes a lot more wiser, is ready for another round of the same data coming in.
I think lots of people doing the GRU instead of the LSTM. So do you want to comment on that?
I have seen the other way around. I've seen a lot of people using LSTMs than GRUs. In my at least, I've referred at least some 10, 15 papers here. Almost all of them are LSTMs, except the reread model I was talking. They did both LSTM and GRUs. But my experience is not many people using GRUs. There seem to be an opinion, I don't know if there's done a controlled study or not, there's an opinion that GRUs are slightly faster because LSTMs has 4 gates and GRUs has only 3 gates. So the computation is slightly lesser, 25% lesser. But if you compare the accuracy and the computing time throughput, I don't think there was a spectacular difference that people were more gravitating towards GRUs. I would say people, I think, are using LSTMs a lot more, in my opinion. Yeah.
So you said generally there are 80% here.
Oh, okay.
80% effort is spending to clean the data. So is there any recommendation to clean up the data, or
Spend
some
80%
general
of the
rule
time.
or tools?
the tools, techniques are so data dependent. Let's say you are a translation company, you're trying to do a translation, and you're trying to create data sets. First of all, there are open source data sets, you can use that, you can train the model, but you want to really have that edge for your model, so you are getting translations. What you do is you actually hire a company which will do the translation for you. Depending on how good the company is and what type of translations they are doing it, you get a good data set or a bad data set. So there, whatever quality enhancements you can do by training those translators and getting the right language skills of the people, not just going for a cheaper company, but a good company, all of that stuff would be some best practices I can think of when you get a real good data set. But let's say you are having sentiment analysis, and for sentiment analysis you want to get the tweets, and there are lots of tweets coming in, especially if it's a very controversial or a exciting product, and the amount of tweets coming in is very fast. You have a pipeline that's coming in, you have a Spark Apache maybe, Apache Spark which is taking in, storing it, you're doing processing. How quickly you can process, how efficiently you can process, how much of the data you really want to pay attention to, how much data you want to ignore, how much data is correct. You may not know. For example, you may get a tweet which is not relevant to your product, but someone made a, let's say your company is Tesla, but someone is talking about, in academic world, someone is talking about Tesla as a inventor about electricity, nowhere connected to, referring to the company. But that tweet comes into your pipeline, you will still process that tweet too. But if you have such erroneous or noise, more amount of noise, then you have a problem. How would you figure out? In this case, I don't think there is any other way of humanly possible, because you have millions of tweets coming in on a daily basis maybe, you can't do it. Any real-time data, people are not able to figure out how to improve the quality of it, especially for sentiment analysis is one thing which data is coming all the time. You just can't store it, do an analysis. But if it's a healthcare solution or a transportation solution or a IoT solution where you have lots of sensors sending in data, you can figure out how many sensors are sending correct data. Are they the right sensors? You can have a human being sit down and look at the data. And hence, the data quality technique will be so data dependent at the time to see what situation you are doing.
Okay, so it's a very like application or user dependent. It's a lot of manual work.
It is, yeah.
Okay.
It is. So I can sit down offline with you to talk about whatever use case you have. I can talk about what are some of the situations you need to pay attention to if it's a healthcare, if it's a transportation, if it's a manufacturing situation, or IoT, or airlines.
Okay.
Yeah, there are different ways of capturing the data.
Okay, thank you.
Okay, anything else? Guys, thank you very much, really appreciate it. One more time, I apologize for not giving the instructions to you in time. It's not Junling's problem, it was my problem. I should have shared the instructions for installation a lot earlier. And also apologies for two errors. One is I could not explain the code I think gentleman was asking, and I made an error on the count semantic analysis code. Sorry for that, but otherwise, thank you very much. Thanks.